Welcome. Hope you've been having a great Devcon conference until now. Our first speaker is a little bit delayed, so we're really sorry about this. Please stay. We're going to continue with the regular schedule, so please be patient, and we're going to start in a couple of more minutes. And nothing, welcome. Enjoy. Well, we are ready to go. Please welcome our first speaker here in the Flowers stage, Odysseus, with lessons from the Nomad hack.
Thank you. Hello. I'm super happy to be here, or not so happy. I would prefer to talk about something else, but we do what we can, right? So first, we have to start with the basics. I'm not here on behalf of Illusory, which is the company behind Nomad. So the views I express are my own and do not reflect those of the company. As it's an active investigation right now, an active incident, we will be not doing any Q&A, unfortunately. My name is Odysseus. I'm a protocol engineer in Nomad. I've worked in Web3 as a consultant, and I've also been working as a DevOps and IoT. So today we'll be talking about Nomad. What is Nomad? How the protocol works. We will need that to be able to talk about bridges, how they work, and the incident. Finally, what are the learnings we have? What did we learn from losing about having a hack that resulted in $190 million in tokens being evaporated? Nomad is not a bridge. Nomad has a bridge, right? But if Nomad is not a bridge and has a bridge, what's Nomad? Nomad is an optimistic protocol, first of all, which means that it has an optimistic security model. It's a protocol for interoperability, which means that it allows applications to be able to meaningfully react to an event that happens in another blockchain, right? Meaningfully. That's super important. We don't define how your application will react to some event. Basically, the Nomad protocol will just send arbitrary bytes from one domain to another. So it's you, the developer, to interpret those bytes. So Nomad is an optimistic protocol for interoperability that supports arbitrary messages between domains. How Nomad works. The first thing you have to know about Nomad, and probably the last, it's that it's super simple. On the sending chain, all the messages that are being sent, they're added to a metal tree, right? So, and why we do that is because it's very easy with a metal tree to prove whether a message belongs to the tree or not. The information of inclusion, in theory and in practice, is included, is compressed into the root. So the protocol only has to do is to send that root from the sending chain to the receiving chain. If we do that securely, then anyone can go to the receiving chain and prove that the message indeed belongs to the tree that has that root. So all that the protocol does really is just passing this root from the sending domain to the receiving domain. Domain is a chain, right? Let's see the life cycle of a message in Nomad. First, we go to the home contract. If you see here, the home contract on the sending chain, and we send the message, right? Then a new route is generated. Then that route is relayed to the receiving chain, and it will find itself in a contract called replica. Then we must wait for the optimistic window to pass. Afterwards, we can go to replica to the receiving domain and say, hey, here's the proof of inclusion, here's the message. I want to prove that this message was indeed sent. And after we prove a message, we can process it. And when we process a message, basically the replica contract will take the message metadata, call the contract destination contract, and pass the message payload. Super simple. Now that we have, in a very basic sense, understand how Nomad works, let's talk about bridges. What's a bridge? A bridge is a super simple application built on top of any interoperability protocol. Basically, you go to the sending chain, right? Let's say Ethereum. You go to the contract and say, hey, bridge, I want to send my native tokens with, for example. It's a native token to Ethereum. It has intrinsic value. And I want to send it to Evmos, right? Then the bridge will hold that with, and it will send a message to the receiving chain, to the Nomad bridge at the receiving end and say, hey, you should create a new MAD-WITH, a representation token, which doesn't have any value in itself. The value is derived from the fact that we can do the opposite. That the user that has the MAD-WITH can go to the bridge and say, hey, I want to burn that token, and I want to transfer my MAD-WITH back into Ethereum. So the bridge will send a message back and say, hey, unlock a new WITH. A hack is when all this locked collateral in the bridge is stolen, right? So now all these representations that are flying around, they're essentially worthless because they can't be redeemed for the original asset, for the asset that has intrinsic value. And I think that's why we're seeing so many hacks in bridges. Not only because they are indeed complex systems, and they are, but because also they have so much collateral locked inside them. They're very juicy targets. They make good targets for hackers to pry and test for the vulnerabilities. Let's talk about the incident. How was the Nomad bridge possible to be hacked? We'll talk about two mappings in the replica contract. Two mappings was all it took. The first mapping connects a root to the timestamp that says that after that timestamp, that root is indeed valid. You can start proving messages against the root of the Merkle tree. Right? So a new root comes, and a new timestamp is generated. So now I can go to the replica, and if the time has passed, I can say, hey, here's the message. Here's the proof. I want to prove it against a valid root. And if that happens, then the message is proven. Now the message, when proving a message, you connect the message, which is byte 32, to the root, which was proven under. Solidity and the default values of mappings. All the default value for byte 32 is 0, and for a number is 0 as well. So in a way, if you look at the second mapping here, in a way, all messages are proven under the 0 root, proven. But of course, in the code, we set an authentication flow that said that, of course, this is not a valid. Of course, this is 0. And if the timestamp is 0, then it's not valid, because also the number 0 is the default value. The problem is that when we deploy the contract, we set that to 1, non-zero value. So what this results is that the root 0 is active after timestamp 1, and all messages are proven under the root 0. So all messages are proven against an active root. So what the users did, they forged messages that were meant to the bridge, that told the bridge, hey, unlock that collateral, and since any arbitrary message that has not already been proven is proven under the root 0, they could prove and process whatever they wanted. And that's right there, 190 million bug. So why did it come up now, right? The Nomad protocol has been active for months. We had an upgrade. And during the upgrade, we changed the semantics of the second mapping. So we used to store an enum here, right? Numbers. So if the number is 1, it's proven. If the number is 2, it's processed. So we didn't connect messages to the roots under which they are proven, right? So even if the root was active, through the authentication flow, we made sure that we didn't authenticate that. But we changed the semantics. And that is why the bug was so hard to find. Our testing didn't find it, our auditors didn't find it, because it needed the old state with a new code. So old state with old code, secure. New state with new code, secure. Old state with new code, not secure. Nomad now. Now the protocol is paused. We'll restart the bridge. That's the hard part. How do we restart an uncollateralized bridge? We'll be sharing more information soon. The TLDR is that users will be able to access, to collect some of the recovered funds as the recovered funds continuously flow into the bridge, and they will do so fairly. You'll be able to read more about it in our coming weeks in our blog posts and Twitter accounts. So what did we learn? What did we learn from this? I like history. Bismarck says that stupid people learn from their own mistakes. Wise people learn from the mistakes of others. So be wise. We'll talk about not improvise and adapt and overcome, but we'll talk about test, observe, engage, and communicate. You can think about as different layers in the defenses of a castle, right? Hopefully, these layers of defense will stop the attackers from reaching the citadel, the king or queen. It's like the Swiss analogy, security. I'm sure most of you researchers will know about that security analogy, but I think castles are way cooler than cheese. So that's why I prefer to do castles. Yes, the bread and butter of every developer, right? Although there weren't any best practices, I think the industry is now slowly aligning on these, on some, best practice on this. So we're having the unit tests, property-based tests, integration tests, forking tests, and invariant tests. And I want to go a quick rundown through them. First of all, concrete tests, super simple. I want to make sure that the function, if I give it 5, I will get 25. We also name it a concrete function, concrete tests. Property-based tests are more advanced. They force you to think about the properties of your code. So basically, to verify that this function will give the input multiplied by 5, always. Then we have the integration test, where we want to test bigger picture, features, user flows. Forking tests, which is like a Web3 specialty. All the other tests, you can find them in other paradigms. A forking test basically could be an integration test or a unit test, but we test against the on-chain state. And this is very important because, as you saw, a bug can surface itself only using the on-chain state. And finally, invariant tests, my personal favorite. Invariants are these equations, phrases that should always hold for your protocol, right? If that phrase doesn't hold at some point, the protocol should be paused. The protocol has broken in some way. So this is a big project. You'll do it in 2 phases. First phase, you will define the invariants. So it's a very theoretical phase, not easy, definitely. And then it's testing the invariants using any tools. There are a lot of tools out there. For example, in Nomad, the invariant that broke was that all messages that are processed, right, received, must have been sent. People were processing messages that were never sent. This invariant broke. And finally, I would like to mention static analysis tools. This could be very useful, especially for newer developers, as they can find some simple vulnerabilities. And storage layout analysis. Basically, you can use tools to verify that the storage layout of your upgradable contracts will not change without you noticing. And this is a very common source of vulnerabilities. In my view, you should prioritize unit tests, obviously, property-based tests, and forking tests. This should be your primary focus with tools like Foundry. I think it's easier than it used to be. Of course, you should always audit, do an audit, although it's not a silver bullet, so don't just do audits. And of course, always check the storage layout, always. Observe, the second pillar. Now we have tested. Alerting. If you receive a UAP message and you aren't already up, it's too late. Like your alerting has failed. You shouldn't wait from a certain Twitter account to tell you that there's a problem with your protocol. This is a solved problem in Web 2. Web 3 will like to invent things again and again, but it's a solved problem in Web 2. So go and read the Google SRE handbook. You'll get a ton of input. Also, talk with your DevOps engineers. If they have worked in Web 2 before, they will have a lot of insights for you. You should start with an object, the business objective, and then define actionable alerts. Actionable, that's the key word, actionable. That means that if an alert A is activated, then you should do B. It should be a very simple if-then close. You should have a playbook for every alert. So if alert A happens, you should do that, and that's the way you should do it, and here's the script you should run. Super simple. If you don't do that, you will get alert fatigue, because you will start not paying attention to alerts, because it's not that important. And by not paying attention, you will miss that alert that will wreck your protocol. A nice mental model for alerts in Web3, I think, is heuristics and environment-based alerts. Heuristics are rules. They require human intervention to understand whether that's a false positive or not. Environment-based alerts, where you have an off-chain agent running and continuously checking the variance of the protocol. More complex, but can be automated, because environments shouldn't produce false positive. Like, if the environment alert is on, that means that either you didn't define the environment properly, or B, protocol is broken. In other way, probably it's a good thing to pause the protocol. Now, engage. Testing has failed, alerting, maybe. So now we're engaging. We are in the first minutes of the incident. What do we do? A poet, Archelaus, told us that we do not rise to the level of our expectations. We fall to the level of our training. So if you don't have an incident playbook, if you haven't gone through that, you will not be able to act appropriately, and you will get wrecked, even if your alerting was good. So a good incident management means explicit ownership. Very specific persons should have very specific ownership of the management of the incident. Outcomes. Every person should know what should be the outcome of their work during an incident. Game day, game day, game day. Do that again and again, go through simulations. The entire organization should create game days for these incidents, because they will happen. They will happen. And you shouldn't be, during the incident, you shouldn't read the incident playbook for the first time. Jörn internally has a very nice blog post about it. I highly suggest you look at it and you adapt it to your organization. We didn't engage in proper time. We lost money, right? So it's now time to face the music. What do we do? I'm sure everyone would like, yeah, let's talk to the users. We have to be transparent. We have to tell them what happened. We have to be, tell them before they read it and wrecked. No. Nope. You shouldn't talk to anyone. You talk to your legal team. You don't do a commit. You don't do a tweet. You don't to your mother. If you don't with your lawyers. You should think about what the users want. But you should talk with your lawyers first. When you do communicate, you should be honest. No sugarcoating, you just insult them. You should have pre-approved messaging, because that's easier. Like during a crisis, after the first hours, you're shaking, you haven't slept, you're high on caffeine, you can't properly create a communication or a PR output. You should tell them what you do, what are you doing right now, and what you plan to do. Let's see a quick timeline of the first days after an incident. First of all, we talk with our lawyers and we inform them of the situation, so they can start talking with law enforcement agencies for asset recovery. We do the first batch of public communication. We tell them what happened, what we want to do, what we're planning to do. We talk with our partners, ideally through more privileged communication group like Telegram. Maybe we can share it more than we share with the public because of NDAs and all that. Because as you are losing money, they are losing as well. Then you should talk with a chain analytics firm. That is very important. I will tell you why. Because apparently people, they suddenly have a change of heart when legal enforcement agencies are zeroing in on their real identities, right? Suddenly they just want to return the funds back. And the only reason and the only way to recover assets is using a chain analytics firm that will go on and analyze all these transactions and find correlations. And they will be able to point the law enforcement agencies to centralized exchanges so they can freeze funds and request data, personal data. So if you want to recover your assets, you will need a chain analytics firm. Then you will set up a recovery address where you can you will start collect the funds and align with your team on the bounty. And of course, the bounty has many legal externalities. So again, your lawyers will be your best friends. We will not do any Q&A, so
we have time for one question, so...
we will not do any Q&A.
No, we don't. Unfortunately, we don't have time for the Q&A, but if someone has one question, we have time.
No, we will not do any Q&A.
With what? Sorry?
We will not do.
Ah, okay. Okay, so no Q&A. Sorry, excuse me. Thank you so much, Odysseus, for your time, for your presentation.
Bye.
It's time for our next talk, Decentralizing Infura with E.G. Galeano and Tim Myers. Please give them a big applause.
All right, here we go. Hi, everybody. Hey, Patricia. My name's E.G. Galano. I'm one of the co-founders and the general manager for Infura, and I'm joined today with my colleague, Tim Myers, one of our lead engineers at Infura. So you've seen the title of the talk. You might have caught our announcement at ETH Berlin a month ago. We're here to talk about decentralizing Infura. It's something that's been on the Twitter waves and crypto Twitter for years, something that people ask us about all the time, like, is Infura centralized? How are you going to decentralize? Are you going to decentralize? This is the talk where we answer quite a few of those questions for you. We gave you a preview at ETH Berlin, if you're able to see the recording from that talk. This is going to go more into the details of the why behind it, the why now, what now, and especially the technical details that go into decentralizing Infura. So Infura was launched in 2016 with the sole purpose of providing utility for Ethereum and IPFS developers. It's something I say in all of my talks because I want to make it very clear that Infura was always about the developers and making sure that developers that are building on Web3, which for us was initially Ethereum and IPFS, could quickly get started. And we did that at Devcon 2. It was 4 of us from the Infura team. We flew to Devcon. At the time, we were a small team within the larger consensus organization focused on trying to build something that would be useful. And so we all went to this conference, and we were saying that we were going to get up on that stage and say, there's a lot of innovation that's happening in this space. We've created this new service called Infura, and it's a traditional SaaS service that you can use to connect to blockchains. And we had a lot of apprehension about that. Like, what would the reception to that be? Because at the time, we were all running our own infrastructure. We were all running our own nodes. There was very much a lot of interest in light clients, verifiability of data, and we were saying, don't run your own infrastructure, trust us to run your infrastructure. And so the reception at Devcon was a little mixed. Some people were like, okay, great, I'm going to use that. Other people said, but why would I want to do that? I can just run my own node, and it's going to sync in an hour, and then I don't need you anymore. And so we said, well, that might be the case, but we're going to try it. Like, we're just here to try to provide something useful, and maybe it will be useful, and maybe it won't be. And so we went up on stage, and we announced that we were going to be doing this. And then during Devcon 2, the Ethereum network was subjected to the denial of service attacks that almost brought down the network. And many of the heroes that helped save the network from that are either in this room or definitely at this conference, the people that helped mitigate the attacks on the network. And Infura's role in that at the time was trying to keep our endpoint up that was already being used to serve MetaMask. MetaMask had launched 2-3 months beforehand, and thousands of users were already using MetaMask every day to send Ether, do some basic interactions with some of like the early maker contracts that were out there, some of the early other experiments that were out there around that 2016 time. And we said, well, we can't do anything actively to fix that client. We're not the protocol core developers. The core developers are solving that problem. But there was already this issue where we were in Shanghai. The Wi-Fi there was awful, even worse than at most conferences. And nobody was able to like get access to their infrastructure to update their clients once the actual client development teams had put out these updates. And so our Infura team was sitting there in the lobby of the hotel, updating our endpoints so that the thousands of users that were using MetaMask that might have been pointing MetaMask at their own infrastructure could use Infura until their infrastructure came back online. And so that started to highlight one of the value props that we saw, which was by having this centralized point, we could simplify or try to eliminate a lot of the pain for these users by, yes, we'll take on this like aspect of centralization, but for the most part, it'll be beneficial. And we said, we're going to keep doing that until it gets to the point where we feel like it's crossed a tipping point and we need to try to do things differently. And when you look around the space, there's other points of centralization that have paths to decentralization. Things like fiat on-ramps and centralized exchanges, and how there's a transition from those to alternatives or decentralized, truly decentralized ways of doing the same operation. My favorite example is when you talk about rollups and how initially rollups start as having a single entity that's creating the rollups, and the rollup teams have a roadmap of how they will eventually get to being more decentralized. So that's how we thought of ourselves as Infura. Start as centralized, and we'll see when we get more decentralized, and we're going to have a solution for how we do that. And the reason is because we had to create quite a bit of proprietary infrastructure to serve the traffic that we've done over the last 6-7 years. What we run today as Infura is far more complex than what we ran with in 2016. If you had tried to replicate what we had in 2016, maybe a month or two after we launched, you could do it within a week or two. Now it would take you probably years to try to replicate the systems that we've had to build, because between 2016 and now, we went through the 2017-2018 ICO bubble, the 2019 crypto winter, 2020 DeFi summer, all of the explosion of NFT growth, and with every single one of those things, you might have run into an Infura production incident, something that showed, oh, this didn't scale exactly right. And every time it didn't scale exactly right, we improved our system, right? And so it forced us to innovate every single time. Take data, like back in the day, we used to send requests directly to Ethereum nodes, and there was really no virtualization, as we call it, custom services that would handle the traffic, because we didn't ever want to be in a position of providing the wrong data to you, because that would be really bad. That'd be the end of our service if we ever provided you the wrong data like that. And especially in 2021, we ran into this issue where we tried to be very conservative with how often we updated our clients, because early on, the clients were a little bit bleeding edge and a little bit unstable the closer you tracked to the latest release. And because of that, users were complaining, like, maybe give us a little more stability, less of the absolutely latest client. That ended up biting us in 2021 when we were running a client that was about 6 months old, and a bug was triggered by a team that I won't mention because it was an accident, and they apologized to us. But it took down Infura for 6 hours, and that was our first multi-hour outage that we had ever had, and it's still our worst outage that we've ever had. And so that really made us think, maybe that was the tipping point. Maybe that's the point where we need to start considering now's the time to do things differently. Because for us, decentralization was always the plan. We said, we're going to get there. It's just not the first step in that plan. We said that we were going to set out to prove that Web3 could be served by SaaS. We're going to say that we're going to run a SaaS service, and that's going to be beneficial for the ecosystem, and it's going to bring more developers in. It's going to bring in more investor interest. A lot of activity is going to come into the space because people will see, oh, I can actually make a living and support myself running a business in Web3, when at the time it wasn't very clear which models would work. And so now, Infura is not the only game in town. There's dozens. Like, they can't even fit on this screen anymore. And we feel like we've accomplished that goal. We've proved that SaaS works in Web3. And so now we want to prove that Web3 models can be used to serve SaaS. And that's what we took as our approach to decentralizing Infura, and that's where we are today. And the first step to that is open collaboration and transparency. We don't have the entire solution in a white paper form that we're going to upload to IPFS and you're all going to read it right now. Like, we're still in that design phase, but we've already started collaborating with other people in the ecosystem on that design. We've been working on it for a year and a half. This is where we want to start showing you more of the technical details of what goes into that. What does decentralizing Infura look like? People have said, oh, are you just going to create a DAO so that we can have some governance over what Infura does? Is that good enough? Or is it some sort of utility function that we're going to try to have as part of this network? What are the incentives of participating? How do we incentivize the right behaviors? And what people were especially asking was, does participating in this decentralized infrastructure network mean like Infura still owns and controls everything? And that's the biggest question that we got in the last month since we announced at ETH Berlin. And the answer to that's no. That defeats the purpose of what we're saying with a decentralized infrastructure network. That's supposed to be a permissionless network. So Infura is going to just be a partner in a decentralized permissionless network, one of an equal amount of, or one of equals in operators. So now I'm going to pass it over to my colleague Tim, and we're going to start sharing some of the technical details with you.
Thanks. Oh, sorry. Yeah, so as EG mentioned, we don't have all of the details of this figured out yet. We're still pretty deep in the design phase. But the next 10 minutes, I'm going to try and walk you through as much as we have figured out right now as I can, and then hopefully save about 5 minutes for any questions you all might have. So first, I want to start with just a really high-level overview of what we see as the network participants in this decentralized Infura network. So first, of course, you have your end user who wants to connect to a Web3 network. Maybe they just need to send a transaction to a blockchain. Maybe they need to read a bunch of data from it. Either way, they need some way to access the API that a blockchain node typically exposes. And so the first participant to support that are the infrastructure providers, of course. And they're the ones that are going to actually be running the blockchain nodes, all of the supporting infrastructure that makes that possible to allow for high throughput of requests to send all the transactions, to read historical data, all of those things that you typically do with the centralized provider. And they'll provide this service in return for a reward, which is what's going to motivate them to want to do this. The next participant, we're calling the network status watchers. This party will provide performance and capability reports of the infrastructure providers. So they'll be there to kind of check and keep them honest. You know, they'll see that they're keeping up with the head of the chain. They'll check that they're responding quickly, that their answers are accurate, all of the things that you would hope that an API does. And finally, we have this concept of an ingress node. They kind of act as an intermediary. They will sell the actual network resources to users after purchasing them from the infrastructure providers. And later I'll also show how they're not entirely necessary, but they can provide a UX option that I think is useful. So more detail on the infrastructure providers. The first thing, of course, to note is that instead of now with just a single centralized provider, we'll have many of them, and they won't be run by a single party. So here we just have a little simple diagram. We have Infura. We'll probably run one, of course. You'll also see other named providers that you're used to seeing that we hope will collaborate with us. And you might also have anonymous providers, so you never really know who they are, but through the mechanisms of the network, you can come to trust that they are going to provide a good service. So these infrastructure providers, they commit to providing capacity on the network. They'll specify the protocols and capabilities that they support. So we envision this network working for Ethereum, but we also envision it supporting all of the sort of new networks that Infura has added over the last couple of years, the layer 2s, new layer 1s, but not every infrastructure provider is going to want to serve all of those. So they can pick and choose and specify what they want to support. They'll also say the capabilities. So you might be used to having archive nodes for Ethereum, and then sometimes you need that, sometimes you don't. And running archive traffic is a lot harder. So some providers might do that, some might not. They'll also give an idea of the amount of throughput that they're capable of specifying. And this may take a couple different shapes, but you can think of it as like 1,000 requests per minute. When someone registers as a provider, they're saying, I can support this much, and so that people can then buy that back. And of course, they'll be compensated for doing this. I want to talk a little bit about what it actually looks to be a node provider. And so this is a diagram of what Infura does and what other big centralized providers do. It's complicated. As EG said, it's become much more complicated since 2016. To start, of course, you have your blockchain nodes. These are the ones that are produced by the client teams that interact with the peer-to-peer network, that sync blocks, that verify it. But there's a lot of supporting infrastructure around that. So first, we have a snapshot system. If you've ever tried to sync a node, you'll know that it takes a very long time. So we typically take the disk of a blockchain node, save it to our own private secure storage, and then when we need to horizontally scale out those nodes, we use that as a seed for new blockchain nodes. So it's downloaded onto a server and then synced from there, which makes it much faster. You also have various indexers and accelerators. So if you've ever tried to do like a big, wide get logs query for events from a blockchain node, you'll know it's really slow. So we have special indexers to speed that up, also for things like NFTs. In front of that, you have a load balancer that makes the decision of what accelerators to send your requests to. Maybe for just sending a transaction, it goes directly to the nodes. And then in front of all of that, we often have a consistency system that helps make sure that users see a canonical view of the chain. So this helps with reorgs to make those a little less painful for the user, and also make sure that if they like query a block, it doesn't change in between requests. And this is something that is altogether quite complicated. There have been several projects out in open source land that have attempted to help with this. I think most of them are more on just running the blockchain nodes, running several of those, but to really provide good service, you need a lot more than that. And we will be releasing our own open source infrastructure kit that node providers can use to help them participate in this network. Of course, there's also going to be parties that already know what they're doing and will probably just run their own flavor of infrastructure to provide the same service in the end. Next, we have the network status watchers. Again, there's multiple of these run by different parties. These will periodically test the infrastructure providers by sending them a small volume of requests. They'll measure the performance and check for correctness of those responses. They'll report all of this to a federated status page. So if you're thinking about using this network, you'll be able to go there, look through the different providers, see how they perform, what their capabilities are, all of those things. And also in cases of provably incorrect responses. So there are certain requests on the Ethereum JSON RPC API that you could prove with Merkle proofs rather easily. So in those cases, those might also be used to inform penalties to the node providers. And we hope over time, as stateless clients start to improve, that there will be more and more of that API surface that is verifiable. A picture of kind of what it looks like to run a network status watcher. They will have to run some small amount of blockchain infrastructure themselves, not nearly on the scale that an infrastructure provider would because they're not serving a high volume of requests, but they need sort of a baseline to compare to. They want to check that the infrastructure providers are near what they think is the head of the chain. And then, of course, they'll have all of these periodic tests that they're running to see if the providers are operating well. So they'll interact with the infrastructure providers. They'll potentially send things to a smart contract on chain for those provably incorrect responses. And then they will also send their results to a federated status page where you can view more detailed information. And then last, we have the ingress nodes. So as I mentioned, this kind of serves as an intermediary between the end user and the infrastructure provider. So an end user will send their JSON RPC request to an ingress node, and then that ingress node may then forward that to multiple different infrastructure providers. Maybe they generally send it to one, and if that goes down, they have a fallback. Maybe they round robin. Maybe they choose to actually send it to all of them and do a quorum of that and return it to the user. This will be something that the ingress node can actually choose how they want to do it. And one reason for having this ingress node is that you can use it to give the same Web2 UX of the centralized providers today. So I think there's a reason that Infura and centralized providers have been so successful. It's provided an easy entry point for people to come and swipe their credit card and get access to the network. And that doesn't necessarily align with the decentralized ethos, but it's also brought a lot more people to our world. And so an ingress node might allow users to actually pay them in fiat and then give them API access. But this will still have better results than the current model because they can then be sending the traffic to multiple infrastructure providers and get some of those benefits. In addition to that, though, an ingress node might purchase resources from several node providers and then register themselves as a node provider with the sort of the sum of all of that capacity. And then an end user can go and pay for that provider in crypto. And then you have a fully crypto native experience. So there's options here. The node provider lets you do a lot of interesting things with combining other providers. So the on-chain registry is what we're typically calling our smart contract that kind of coordinates all of this. And the main way to think about it is it's basically the data structure of your node providers. So we have a very simple example of what that kind of looks like. This is just one detail, but you have your named providers and the protocols that they're supporting. So as Infura, maybe we're supporting the 5 that are listed here, but maybe operator A is only supporting ETH and Polygon. This is where you would also be able to see things like maybe what region they exist in, whether they support archive nodes, things like that. Going to look sort of the timeline of how this all operates. So first, of course, the smart contract is deployed. Some amount of time later, your infrastructure providers come in and they register. They specify the protocols, the capabilities, and the throughput that they'll support. Some amount of time later, you'll have network watchers that will register. They may only want to participate watching for certain protocols. Maybe they're only capable of checking certain capabilities. Maybe you have a watcher that can't check that a node or that an infrastructure provider can support archive access, but they want to help with the near head requests and see that those are good for providers. And then finally, you have your consumers who come in and purchase throughput. So that might be an end user who wants to go directly to a node provider, or it could be an ingress node that wants to combine them. And once you put all of that together, you get sort of what we view as our decentralized architecture. So in the center, you have the on-chain registry. You have your network watchers, your infrastructure providers, your blockchain API consumers, and your ingress nodes that all will register with that on-chain registry. And then once that's all set up, your blockchain API consumers can send their requests to the various infrastructure providers that they've chosen, or to an ingress node, which is sort of helping them do that. And yeah, we hope once we have that all figured out that it'll give us a self-sustaining, reliable, and robust network of infrastructure providers that's built to really serve the high throughput that Infura can today, or other centralized providers can today, for all of the blockchain API requests that you need. But instead of what we have now, it'll remove a single point of failure. We hope to do this out in the open as much as possible and really follow that collaborative Web3 spirit. This is, we hope, really going to improve reliability for the users and get a lot closer to that kind of 100% uptime dream. But also, which I think is important, still provide the ability to have that really easy Web2 UX if you want it. We could also have the crypto native. And yeah, that's it. We're seeking strong Web3 infrastructure providers to work together with us. If you're interested in joining and participating in this network, I encourage you to snap this QR code. It takes you to a form that you can fill out, provide a little information on your experience and your interest, and we'd love to work with you. That's it. I've got about 4.5 minutes for questions if anyone has any.
Thank you so much. Please raise your hand if you have questions so our volunteers can lend you the microphone.
Ooh, 1, 2, yeah. So do you plan this whole decentralization to be more curated or censorship resistant?
Sorry, what was the first? You said censorship resistant?
Yes, so either you have, for example, a list of curated providers for quality, or you have a censorship resistant list of providers that will treat any request from anyone regardless of...
Definitely improves censorship resistance because it's permissionless. Anybody can participate in the network by meeting the criteria to join the network, which is technical criteria of meeting a level of performance. Right? If you can meet a level of performance, you can participate in the network. We're not going to be selecting who can participate.
And then as a consequence, what if a provider constantly performs badly?
They would be penalized by the network, right? There would be a financial incentive to provide the minimum level of performance, and they would get penalized by the network if they're not meeting that level of performance. Additionally, that network watcher or status monitor that we're talking about is continuously checking and reporting on both the capabilities of the network as well as the performance. So you can see, here's a new provider that just joined. They've only been part of the network for 7 days. They support 7 networks. Of those 7 networks, this is the performance criteria of that, right? And all of that's going to be published in a stream of information that people can consume from to make routing decisions. So a user can, like a very technical user that wants to be in control of that can say, this provider's coming from this region, or this provider's coming from that region, and this is their performance, and make selection criteria of how their traffic gets routed. Or they can pick their level of decentralization and ease of use by going through an ingress operator that can make those routing decisions on their behalf.
Can you give an example of what the centralized infrastructure currently looks like in terms of like number of servers and bandwidth and so on, and what you expect will be when it's decentralized? Will there be overhead? Will it need more servers to do the same performance, that kind of thing?
By number of servers, are you talking about Infura's current architecture?
Current, yeah.
Dozens of subsystems, hundreds of different instances or servers providing different types of functionality. So like we have a separate subsystem that all it does is index event logs, And when you query events from like ERC20 token events and things like that, it's pulling from that subsystem. And then we have this consistency system that tries to keep all of that in sync when you're querying one subsystem versus another. So that's the challenge that we've had, is we built that as quickly as possible to solve problems, and it's very proprietary, cloud specific. And we've been working on how do we retool that so that it's something that can be not just open source and something that somebody else can run, but can run with like not a team of dozens of operations people. And so it's not, what we're going to release in the node kit is what we think is a minimum level of functionality, of performance, where this is better than running a bunch of nodes behind a load balancer, because it now has some of these indexing and performance optimizing systems. But it's something that can be taken on by hopefully an individual, but at the very least a small team, much smaller team than the current Infura team.
Do you think it's likely that this on-chain registrations of the providers will be a new, yet to be launched dedicated chain, or is it more likely that it will be on an existing chain like the Ethereum mainnet?
That's one of the things that we've been considering as we're going through the design. We're leaning towards don't start a new chain for that. Like, try to use something that exists. And that goes back to the why are we doing it now rather than in 2016, when people are talking about like micro payments between providers and like, do you use state channels for that and all these other things. Like, we would have had to devote a significant amount of our research just on that problem, whereas now a lot of these primitives are out there and we can try to use some of the things that already exist to build the network.
Yeah, can you tell me who is the entity or people who decide what the requirements are to become an operator, and who decides which operators or providers would meet those requirements, and then how they would change in the future?
Okay, so multi-part. So who decides who can be an operator? So this form to sign up is to participate in like a permission beta, similarly to like how when other people are developing new networks, we're going to have to start with a small group to try to test and iterate with. And for that, we're looking for people that already have experience with the infrastructure and that we can reach out to and get feedback from pretty quickly on the technical front. But once we actually launch this network, it's fully permissionless. The criteria of that is what we're defining as a protocol in the design of this would be, you know, the amount of resources that you would have to provide, or this would be the minimum level of performance. So you have to at least support one network. You have to at least support this level of performance. And then as long as you can meet that, it's anybody.
Hey, Lefteris here from Rodkey, right in front of you. I just wanted to ask about the ingress nodes. Will they be a requirement or will they be optional?
Did you say like the indexing nodes?
No, ingress.
Oh, the ingress. Yeah, it'll definitely be optional. So I can't quite get to the slides, it'll take too long. But you can still have a consumer who will go directly to the contract to purchase resources and go directly to one or multiple node providers that they choose. The ingress node is kind of an option where if you don't want to go to the trouble of doing that, maybe you want to use one that allows you to pay in fiat, that you can, but it's an option.
This was our last question, but if you have more questions, please reach out to our speakers. We're going to be here. Thank you so much. Please, everyone, grab your seats. It's time for our next talk, technical details of the opcode compatible ZK VM with Jordi Balina, and please receive him with the big applause.
Hello, I'm Jordi Bailina. I'm the technical lead at Polygon Hermes. And today I'm going to present mainly the public testnet that we published last Monday. First of all, I'm going to explain a little bit how the ZK-VM works, and then we are going to proceed to a demo. How a rollup, how a ZK-VM works from the user perspective. Well, a user should not see any difference like working with any other network. What we will do is, first we will send transactions to a sequencer. A sequencer will already give a state. That means that the state will be final as far as you trust a sequencer. Sequencer, in the first version, is going to be a centralized sequencer. We will decentralize later on. But if you trust a sequencer, this transaction is final, and you have the warranty by the sequencer that this transaction is going to be mined. It's going to be processed. The sequencer will collect transactions, and at some point, will send these transactions to the blockchain. Okay? And then at this point, the state is final and safe. Here, we don't have any proof yet. It's just the transactions are set, and we have the warranty that those transactions are going to be processed in that order. And because they are on chain, they are not going to be changed. So you know that they are final, and you don't need to trust the sequencer anymore. You know that these transactions are final. And in background, in parallel, it's going to be the prover, actually, that's going to take all these transactions, and it's going to compute, it's going to prove that this implicit state, so this state that's everybody can compute, but it's not on chain, because in on-chain are only the transactions. The data availability, if you want, the transactions are going to be processed, but it's going to be converted to a real state. And this is proved by the prover. This is the big difference with the optimistic rollups. In optimistic rollups, you need to wait for somebody to challenge this state. In the ZK rollup, this state, it's become, the prover just set this state, and you know for sure that this is valid. Is at this point where the user can withdraw the funds. So here, the most important piece, or the differential piece of a ZK rollup, is the prover. The prover is a zero-knowledge proof, or if you want a validity proof, that validates the transactions. Which transactions? Ethereum transactions. It's taking a state, it's taking a set of Ethereum transactions, and it's computing a new state and validating that this state is valid. So how the prover is built. So what's inside the prover? Well, the prover is a set of technologies, but the way we built this, we have a circuit, which is a traditional circuit written in PIL, specific language we built for the ZK-VM. That's mainly a processor. It's a generic processor. It's generic. It's with some specifies that, but it's a processor that's built with this zero-knowledge technology. And on top of this processor, we are running a program, we call it a ROM, okay, that actually is an Ethereum, it emulates Ethereum. It actually, this program this program is the one that is actually taking the transactions, analyzing the transactions, checking that the signature is valid, discounting the balances, checking the fees, deploying the smart contracts, executing the smart contracts, and doing exactly the same that does Geth or that does any Ethereum node. Just processing these transactions. All this goes to a prover, and this prover is the one that's verified on chain. If you zoom in the processor, well, we have mainly a processor. Is this ZK processor? All this processor is very tailor-made for the ZK-VM. So it's not like a very generic processor. It's this part that's generic, but there are specific pieces that are made explicitly to be optimal for running the EVM program, the ZK-VM program. Okay? This processor has a ROM, which contains this program that's executed, contains the storage, because the EVM, you should be able to store values and and get the values. It has also kind of a subprocessor that handles all the binaries operations. Here includes addition, subtraction, AND, XOR, XORs, and so on. Has a module that's for arithmetic. This is, in the IBM, it works in 256 bits. So this arithmetic circuit actually does all these operations in the 256 bits. Okay, and then has the hashing for ketchucks and other hashes that are also inside this processor. On top of this processor, there is this ROM. Okay, this ROM is written in assembly. It's a specific assembly for this processor, and here contains all the logic. Actually, it contains all the Ethereum logic that where we are processing here. Here I want to show you just a snippet of code of how this looks like. This is just, for example, the opcodes dup1 and dup2, but here we have all the opcodes. We have implemented all the Ethereum opcodes at this point. And then once we run this, then we need like the cryptographic prover. The cryptographic prover, what we do is mainly we are using Starks with a very optimal way to compute proving systems. We are using Goldilocks. It's a technology from our colleagues in Polygon Zero that makes to build these proofs really fast. And it's a kind of a recursion, so it's a prover can aggregate many proofs. And at the end, this is a Stark, and at the end, what's doing is we are verifying this Stark with a Snark. So at the end, in Ethereum, we are just verifying a normal Groth16 or Plonk proof. It's just a circuit. It's a circumcircuit in the bottom of that piece. So this is the stack, the cryptographic stack for verifying that. Okay, so let's cross fingers and let's try to see the demo. Let's see if it works. If it doesn't work, you can try it. Okay, you can go to public.zkvm./test.net and test it. You will see that's very simple. The demo that I'm going to do is, first of all, I'm going to bridge it. Let me just switch. Okay. So the first thing that I'm going to do is I'm going to bridge. So I'm in Goerli. I'm in Goerli network. I have an account here that's has 3 Goerli already, and it's just a Strike new account that I just created before this. So the first thing that I'm going to do is I'm going to bridge 3 ethers, 0.25 ethers. This is the maximum that we allow here in this testnet, just to protect some denial of service attacks here. And we are just to transfer to the layer 2. So I'm in Goerli right now, so I'm just let's see if Ethereum works. Okay, here we are. Let's bridge it. Ethereum. Okay, so let's sign. Let me just modify the gas fee so that it goes faster. It's too early, so you never know. Save. Okay, and then just send this transaction. Okay. Okay, so we just deposit the transaction. This transaction is mining in Goerli. We need to wait also a little bit so that this transaction is kind of a final, so that this transaction is included. Okay, right now this is already done. What we have done is we just put this transaction in a Merkle tree, and then the root of this Merkle tree of all deposits is passed as the state of the rollup. The sequencer, actually, there has not been any special transaction on chain because the sequencer already takes in account that. Okay, so now let's finalize this. Okay, and this finalize, what it's doing is doing an L2 transaction to collect these funds, this Ethereum in the layer 2. So here, when I push here, the first thing that asks me is just to switch the network. So I'm just switch the network. Okay, I just know MetaMask just disconnected. I think now I'm just signing the transaction I'm just signing the transaction in layer 2. Okay, I just signed the transaction. Let's see if it works. There we go. Here is. Okay, so now if I check the account, I'm in the layer 2. Now I have the 0.25 Ether in the layer 2. Okay, so now let's go to do something with this account. Okay, let's create a smart contract and deploy it in this layer 2. So let's go to Remix. Just gonna use an example, very simple smart contract. Oh, God. This looks like Remix is gone. So let me just reload. Here it is. This is just a very example smart contract. So let me compile this smart contract. Here it is. And now I'm going to deploy it to the layer 2. So I'm going to connect this to MetaMask. Okay, I'm just using this account. And then I'm just, well, this is, I don't know if I'm connected to the last one. Well, just connect here. Yeah, this is the one that I just did. I have the 25 Ether here. So and let's deploy this. Okay, so just deploy this smart contract. It asks me to sign. I just confirm this transaction. See if it goes. Its internet is not like the fastest thing here. But here is, okay? So now here we have the smart contract. If we do a get A, we get a 0. But if we, for example, we set a 22, so this will generate a transaction to set this state variable to 22. We sign it, confirm. Save. Here it is. And I just get the value. And I see here the 22 right here. Okay, so I just deployed that in layer 2 like any other network here. Okay, so what's going on in here? So let's go to the this is the roll-up smart contract in the layer 1. Okay, and here we see two kind of transactions. One are the sequence batches, like here, where here you can see in the data that here are all the transactions that we are setting. Okay, but in parallel to this, we have the batches is the prover that's generating batches, that's actually validating these transactions. And here is where all the magic happens. Okay, here in the blockchain you cannot see much, but here is the proof. Actually, this is the Gross16 proof in this case that validates all the transactions that we have been processing. Okay, so until here is, well, maybe I can give you a bonus track here. So we can go, for example, to Uniswap. Okay, this Uniswap is already deployed as is without compiling and recompiling anything. It's just a normal Uniswap. It's deployed in layer 2, and here we can do, for example, a transfer. Let me just change the account to the first one so that I have some tokens to exchange. Okay, and here I want to convert from foo to bar, just a normal swap. Okay, it's fetching the price. I'm just doing the swap, confirm swap. Now I should sign the transaction. So here we have deployed. So here we have already deployed the full Uniswap version 3 in the layer 2, and all this is verified in the prover. Just confirm that. Okay, now this is confirmed. Now, well, here the Uniswap interface has some, it's iterating, takes maybe some 10 seconds or so to realize that the transaction has been moved. But that's mainly the thing. Okay, so let me go, well, just let me see if it finished this. Just, here it is, okay? So I already do the swap, so I can just check in the swap just like normal, like any other Ethereum transaction. So let me switch back to the presentation. So nothing fancy, right? That's the cool thing. And that's the strange things, even for me explaining. For me, here I'm just feeling that I did a demo of Ethereum. But this is the interesting thing. It's that all this is running, all this is validated in the prover. All these transactions that are really complex, or all the Uniswap transactions and everything, this is validated inside the prover. And this is what this ZKVM and the main importance of this design. You don't have to recompile anything. You just take the code, exactly the same code. You don't have to re-audit anything. You don't have to learn anything. You can use exactly the same tooling. You can use the same language, the same gas model. It's no difference. For developers, they should not notice any difference in deploying, in working with Ethereum or in ZKVM. The only difference should be the gas price and the quantity of transactions that you should be able to deploy. This is a testnet. Please test it. We have been running for this week already. We have more than 1,000 accounts. We have, most of them are just deploying transactions. Some of the projects already tested without any big issue. We have some reports of some bugs that we have been fixed also, and we will continue work. This testnet is a little bit like a baby. It was born last Monday, but it's going to get stronger, and this is the previous stage just to the mainnet. Okay. Here is okay, and what's the limit of the scaling this? We don't know yet. What's clear is not going to be in the prover. It's going to be maybe in the data availability. It's going to be in maybe in the sequencer, in the other pieces. But why? Because the prover can be parallelized. And here the important part, actually, for example, we are running 7 provers at this point, because this week, there is many transactions. Some of the provers have been stopped, so we are just trying to catch up with some of these transactions. But this is the cool thing. We can run as many provers as we want. So if there is a lot of demand, we're just running more provers. And the only thing you need to take into account is what's the cost per transaction, because running these servers are not free. So what's this cost? Well, the cost right now is less than 1 cent per transaction. And this is in AWS cost, which is probably the most expensive cloud service in the world. And there is also a lot of optimizations that are coming. Here in GPU, we believe that we can improve 1 order of magnitude, and there is other improvements that we are working on that. But prover is not the bottleneck anymore. What's missing? Well, not much. So we are fully compatible. We are running all the opcodes. Everything works as Ethereum is. There are some things that we are already implementing. They are not implemented yet, and I'm just listing here, but everything is there. What is missing is the pre-AIP, is the original Ethereum transactions. This is mainly to deploy, mainly Nosy safe, but it's just for these smart contracts that have the same address in many chains. They are using these primitive transactions that they don't include the chain ID. We are implementing those. And then we are not supporting yet the SHA-256, the Blake, and the pairings precompiled to smart contracts, but this is a work in progress. All of them are doable, and we will work in the coming on those in the coming months. There is the audit. I don't want to enter in detail in the audit, but this is probably the most challenging part that we're facing right now. There is a full plan for running these audits. If anybody interested in that, please contact me. What else are we working on? We are working also in the aggregating of the proof. Right now, the aggregators, right now we are running one proof per batch, okay? But we have to run one, so we need to aggregate all these proofs in a single transaction in a single proof, actually. We are working in this proof. This is not that much because we have all the recursion already done, and it's just putting them together, but it's a piece that we need to put there. And we're also working with the EIP 4844 for line sharding. This is clearly the future for the scalability, and we are already working on that. We are very excited on that. I have to recognize that when I read this EIP, I was very skeptical at the beginning, but it's really the way to go. We can implement inside, and it really will go even faster, and it's even better than what I would do. It's just that the only thing is that you need to go a little bit deep to understand this EIP. But it's really interesting. I'm very excited for the scaling. Testing. We're running the Ethereum test suites. Right now, we are at 97% of passing all these tests. There are edge cases that we are still working on that, but I'm sure that very soon we will be covering we will be in 100% of the Ethereum test on that. Roadmap, of course, we just launched the public testnet. We need to audit, and we will launch when it's ready. Here is we want to be enough safe. We want enough sure that 100% safe is going to be impossible, but we want to be responsible, and we want to audit this very well. And when we feel comfortable, then we will launch. A reminder: everything is open source. You can take a look. You can see. You can review. Everything is in the GitHub repositories. And yeah, zkVM is no longer a myth. Here you have the zkVM.
Thank you so much. We have a couple of minutes for questions. So if you have a question, please raise your hand.
Hello, thank you for the presentation. The EVM is not a frozen object. It's living and it's evolving with new EIPs, and we are going to see possibly big change like the EOF or other things like that. And they will be way easier to implement for core devs and for you. So are you worried that some possible EVM change will be hard to translate into circuit in the future?
We need to see which are those changes, and once I see the changes, I will tell you. But there is one thing that, because this is some of the questions that I receive. No, it is sometimes it's more about the upgradability of this. What happened if the zkVM upgrade, and then what happened with the rollup? It will upgrade, and if you want a decentralized system. But here is we need to understand as a community that the EVM at this point is evolving because it's work in progress, but at some point this will need to be frozen. I don't know when and how, and I'm not talking about the zkVM, I'm talking about the EVM. So the EVM, if you want, I believe, I hope, and talking with people with the EF, they already think very much on that time, is that at some point, maybe in 2 years, 3 years, 5 years, once the Ethereum is finished, then the EVM will be frozen, and then it will be also the time to freeze the rollups.
Thank you for the presentation. Great talk. I would like, could you detail a little bit what are the edge cases that you are meeting regarding the failing tests?
Here we have Carlos in the room. That's responsible for testing. You can ask them, but they are very complex one. It's a call of a static call, and then do a self-destruct and do whatever. You know, these are very edge cases, very edge cases tested. But you have to look at it because you never know, and it's important. That's why those tests are there. But are really edge cases at this point, and complex ones.
Hi, thank you for the presentation. When you were showing on the Etherscan the contents of the badge, you showed that there was decoded, encoded set of transactions. Is there any way to decode them to see what exactly is in the badge?
Yeah, it's mainly are the transactions one after the other. we have some internal tooling just to take a look on that. Well, actually, they are open source, so you can check the repositories. But we are building it. And in any case, it would not be difficult to interpret. At the end, it's just a format with a array of transactions.
I think we have time for one more question. So if you can lend the microphone to our speaker. Ah, cool. Go ahead.
Hey, thank you. Can you hear me?
Yep.
Okay. First of all, congratulations. This is amazing. When you launch, let's suppose it's early next year, obviously it's a very complicated system. If you find some bug or something that needs to be addressed, what can you do in that situation?
Bootstrapping decentralized systems is not an easy topic. Here we have the experience of Hermes 1.0 in our team, and here you do some, I would say, nasty tricks. Here is maybe you do an upgradability. Things that you can do is an upgrade. So you can upgrade the smart contracts with maybe with a time lock, and you can do, for example, is limit the withdrawal flow that's leaving the smart contract, so that it's like if you are working with less than a certain amounts, you are purely decentralized. But if you want to run fast and run bigger numbers, then you have the option to go centralized or just or white. And there are some tricks for bootstrapping, but these are just temporary solutions until we feel comfortable. At some point, the roll-up should go along. We are building a decentralized system, and it should be safe enough. Here is how we are managing that in the beginning. Okay.
Thank you so much, Jordi Valina. Please give him an applause. everyone. Welcome to the Flowers stage. It's time for our next speaker, Harry Kalodner, with On the Path to a Rollup-Centric Future. Please receive him with the big applause.
All right, thank you. It is very exciting to be here. DevCon is just such an amazing event, and the energy here, it's incredible. I'm just excited to be able to talk to you guys today. So yeah, I'm Harry. I am the CTO and one of the co-founders of Off-Chain Labs, the company that built Arbitrum. And I'm here today. I'm going to kind of walk you through a bit of the history of Arbitrum and how we got here, where we are today, and then talk some about sort of where we're heading and what the future looks like. So Arbitrum is actually originally came up with really cool history in 2014. Actually, before Ethereum had even launched, one of our co-founders, Ed, had the idea of, hey, this thing is really cool, but it doesn't seem like it's going to scale. Now, at the time, it was very early, and the idea ended up sort of forgotten to history for a little while. Until in 2017, we started working on it. At the time, we were at Princeton University. Academics thought, hey, this is really cool and interesting, and it seems like there might be something that'll really grow here. And we started out. We wrote a research paper back in 2018. It's crazy because it feels like yesterday to me, but it's almost ancient history in crypto time. And then managed to somehow, and I still am not completely sure how, to found a company around it and share it with the community. So at that point, we had this idea. We were building. Back in February 2020, just around East Denver, we actually had the first Arbitrum testnet. It was a lot different than it is now. Actually, we started with technology that looks a lot like, looks more like and included features like our Nova chain has today, which I'll mention a little bit, but it was not a rollup. It had a committee, it had sort of off-chain agreement, but it had a lot of features like it has now, and doing application-specific chains. So interestingly, sort of a lot of where we are now, it was too early then, but there was sort of a lot of ideas that have been bouncing around that I think are now sort of coming out as really popular. And then we went from there. We launched testnets. We figured out arbitrary contract deployment. We figured out arbitrary messaging. We actually got our mainnet out, and this was back in May of last year. We launched our mainnet to developers only. We had a great few months there. And then in August, so over a year ago now, we launched on mainnet. And that is how we ended up building Arbitrum 1, getting it out there. It's been an incredible time since then, but the building never stops. If you stop in crypto, you might as well, you're done. Nothing is ever sort of, research always continues. No technology today will be sort of, it'll all look ancient in 5 years. And kind of Arbitrum, when we launched, already looks ancient compared to Arbitrum where it is today. Because this last year, we worked on our Nitro upgrade, which I'm going to be talking about some today. We launched our Nova chain, which, as I said, sort of actually takes a lot of ideas from our original paper. And sort of the world is now, I think, in a position where they make a lot more sense than they did then. We went through a really sort of challenging and interesting thing, which was the live upgrade of our Arbitrum chain to an entirely new technology stack. And it was really interesting to us. We did it kind of a couple weeks before the merge, and it was essentially our merge. In that certainly not the same amount of coordination necessary, but the idea of kind of taking a technology stack and somehow, while with a running system, actually kind of replace the technology underneath it with a newer version, with a more powerful version that allowed it to be cheaper, faster, all sorts of good stuff, which has made it for a really exciting year for us. So Arbitrum 1, just to kind of jump into like, well, what is this thing I've been talking about? I walked you through the history, but it's nice to sort of dig in a bit more, talk high level. What does Arbitrum provide? Why should you care? Hopefully most people here already know, but it's certainly nice to say. Low-cost transactions, security rooted in Ethereum, so inheriting security rather than trying to have independent security, which is really powerful, which is what rollups give us, and really, really, really full compatibility with Ethereum, which is the thing that only optimistic rollups, at least today, can provide, and means that sort of tooling, languages, everything just works. And it's been really huge for developer adoption. It's meant that the learning curve and the difficulty of applying on Arbitrum has been incredibly low, and it's how we've been able to get so many people involved and have so many people benefit from the technology that we're building. So just a couple stats, and this is actually slightly out of date because the market is down, and this slide was made before the, so I think it's more 2 billion plus now, although the amount of value in ETH, I think, has increased. So, you know, it depends how you look at it. But Arbitrum is going strong. We have a huge amount of adoption, huge amount of projects, huge amount of users, and it's just been sort of incredibly thrilling to watch. It feels as though it's been like forever now, but it was only a little over a year ago that this all became possible. We have a huge ecosystem. We have kind of native apps. We have Ethereum dApps that are kind of have been on L1 and started out there, but then have migrated. We have tons of infrastructure support from all sorts of different companies. Shout out to Tenderly that just launched full Arbitrum support recently, which was very exciting. And Arbitrum is becoming a major part of Ethereum. Two kind of interesting charts here. One being, and it's not rendering very well, but you can look on Etherscan yourself. One being that the Arbitrum sequencer is one of the biggest gas spenders on Ethereum, that we are now sort of using a significant amount of L1 resources in order to power the rollup, which is really exciting. And also very exciting that will hopefully go way down with 4844, which I won't get to talk about too much in this talk, but is extremely exciting. That and the other thing being the amount of ETH that's just in Arbitrum, that our bridge escrows funds that are deposited in the system, and the amount of funds in that bridge is a very significant chunk of ETH, which is crazy exciting. And then the other thing to look at, and this is sort of just, you know, very exciting and also has been kind of vastly improved with Nitro, is how cheap it is to use. I think we're on average coming in at somewhere between kind of 10x and 50x price reduction compared to Ethereum. This has gotten better with Nitro as we added compression. L2 costs are quite low because of all of the efficiencies of the system and the fact that kind of the gas limit can be quite high. And so you can see we have here just L2 fees, which is a very nice site to look at. You can see that we are coming in sort of just a couple cents to transact. In the simplest case, we're doing ETH transfer. And even smart contract execution is very cheap and easy. So I mean, that's one thing always to look at is essentially ETH transfer. It's easy to be cheap, but also to be cheap with contract execution, where users can use a lot of gas and it still comes in cheap is really, really important. And I think one of the areas that I'd say is sort of, especially, of course, this presentation and the last one, obviously, for people who saw both, are covering kind of, you know, similar ideas. And I think this is one place to distinguish optimistic rollups, is that we can do a lot of computation, a lot of execution at very low cost. And just sort of for rollups in general, and this is sort of general across ZK rollups, across optimistic rollups, but I think it's really important to talk about, is just looking at sort of what rollups can give you versus sidechains. So with rollups for data, we are using Ethereum and we're depending on Ethereum for data availability. All transactions get posted. Unlike sidechains where kind of the data is separate, maybe they're posting headers back, but it's an independent system. We have, I might cut for a second, but I'm back. We have L1 to L2 bridging that's enforced through the security of the rollup, and that's sort of one of the most important features of rollups to me, is the fact that the bridge is part of the system. There's no sort of independent multi-sig, no independent bridge mechanism. The bridge is the rollup, which is really fundamental, as opposed to sort of needing some sort of messaging layer that's independent from the security system. The rollups use fraud proofs. Well, validity or fraud proofs for optimistic rollups. Fraud proofs, of course, which means that anybody can prove the correctness of the chain. And it means that basically you don't need 2/3 honest. You don't even need half honest. You would only need one honest validator in order to secure the system, which is an incredibly powerful property, as opposed to needing kind of and then just to mention a little bit, I'm mostly talking about the rollup today, but I want to also mention Nova, which is sort of our kind of version of Arbitrum, but with the data availability committee. There's some really interesting trade-offs here, and it's a kind of a very active design space that I think the whole rollup community is exploring, which is ways to make data cheaper. Posting to Ethereum is the expensive part, and so being able to move that off-chain by having a committee where you're not worried about a majority, you're only worried about a couple on that committee being honest, is a really powerful thing, and it's what allowed us to be able to offer a platform that can really be competitive with sort of other non-rollup systems which don't have the cost of hosting to Ethereum. And it's an interesting trade-off. It does make some sacrifices in security. The way we think about it is that we're not competing with rollups. We think if you can afford a rollup, you should use it. What we're competing with is other solutions that don't have that level of security and trying to provide something more secure than they are. Now just a little bit about sort of how Nitro works and sort of how to imagine the system. A lot of times with rollups, because it's so compatible, it's kind of a black box. You have the RPC, you point at the RPC, you use it just like Ethereum, and that's it. But it's really, I think, valuable to understand what's going on and really important. So we split it up into a number of steps, and we have iterated on this a lot. How do you explain this thing? It's complicated. There are a lot of different pieces. I think the latest iteration is one that we're pretty happy with. So we start off by talking about sequencing, and this is probably the role of the sequencer is one that's sort of most well known in how rollups work. Sequencer is a node that orders transactions. It receives transactions in, it puts them in an order, and then it runs them. It evaluates state transition function, and it produces blocks. Well, that basically sounds like how Ethereum works if you replace sequencer with miners. Although for the sequencer, there's one entity rather than a lot of them. The interesting part is in parallel, or slightly trailing the ordering of transactions, the sequencer is also batching and compressing those transactions and posting it to the L1 chain. Now, one key thing to understand here is that the sequencer is not attesting to state roots. The sequencer is not making claims about what the result of executing those transactions are, like what the result is. All it's doing is saying, these are the transactions. So there's no such thing as sort of claiming something valid. Claiming something invalid. You could post an invalid transaction, certainly, but it would just be ignored by the state transition function and rejected, and the sequencer would be out some money. But it wouldn't have any other consequence. And so that gets posted to the L1 chain, and then picked up by the actual rollup security mechanism, which I'm not going to be able to get too much into in this talk, but there's some great material about online. So what does this mean in terms of finality, which is one of those important questions? Because you have these systems, and you have when MetaMask says, okay, the transaction's in a block, but that's not enough. Finality is this really important question, which is when can your transaction be reversed? It's one of the things that with the merge has changed a lot for Ethereum in very interesting ways. And sort of Arbitrum has its own notion of basically how you can tell when a transaction is final. And so we split it up into 3 phases. We have soft finality, where the sequencer said it's the order. If the sequencer is honest, that's what the order is, but you're trusting the sequencer. And so for many applications, this is actually pretty good. Currently, the sequencer is being run by us. Long term, the sequencer will be decentralized over a number of parties. No need to trust it, but you can, and a lot of people do. After that is kind of the really important mark, though, which is when can you actually not trust the sequencer? Because if you just trust it the whole time, it's a centralized system. And particularly for kind of exchanges, for anybody doing cross-chain stuff, you really don't want to introduce any trust assumptions. And so for that, basically, the idea is that after the sequencer has posted a batch on chain, the order is set. Once the transaction posting that batch itself has L1 finality, the system is completely deterministic. So any node off-chain can get a guarantee of what the current state of the chain is based on batches posted. And so if you're familiar with optimistic rollups, we have, and this is the last phase, this certification process, which takes 7 days. The only thing that's for is to prove back to Ethereum what the result is. Because after 10 minutes, after a batch is posted and finalized on L1, anybody in the world looking at the chain other than Ethereum can know. And the reason for this is really simple. Ethereum can't actually run all the transactions, because then it wouldn't be a rollup and then it would be expensive. Ethereum's not running them. We're using fraud proofs. But off-chain, anybody can just run the transactions themselves and calculate the result. So now that we have that down, what is the state transition function? I mentioned it quickly, but it's sort of a very core part. And that is basically with Nitro, we now have essentially a wrapper around the kind of core Geth implementation of Ethereum state transition function, which means our functionality can be essentially identical with Geth. We don't need to worry about corner cases. We don't need to worry about weirdness and about matching implementation specs, because the Geth team does an amazing job of that, and we can just lean on their work and on Geth's correctness for our correctness, which is really valuable because it's incredibly hard to get all of those corner cases correct, and we don't need to. And then I think the last part that I'm going to talk about today is how execution and proving are different, which is really interesting and really where we get where we can get most of our performance from. And this is something actually that changed with Nitro. Before Nitro, there was a VM, it ran transactions, a result was produced, and that was also a proof. That's very inefficient because proving tends to be something that's very slow. With Nitro, instead, we split up these processes. And so we have basically one core code base compiled in two different ways. One to run at native speed on your computer, at exactly the same speed any EVM chain can, and one compiled to WASM and used for proving, both from the exact same code. So there's no need for kind of multiple implementations. There's no need to worry about, is the client in sync with the prover, and all sorts of weird edge cases you can get into there. It's using the same code. And this is, and I like to show this slide just because it's when we first started showing it, I think it was sort of very recent. Now it's 2 years later, which is kind of insane, which is really kind of how we ended up here and how I think the Ethereum community came to this path, which is the idea that rollups are the way that Ethereum is going to scale. And I think that's sort of really important to us, and really the way we think about it is that kind of, yes, there are multiple different technologies. Yes, we're all building, but kind of really what we're doing is we're empowering Ethereum to actually kind of be competitive against other alternative blockchains. Since those two systems in combination can do much more than other blockchains can do alone. And then just at the end, I wanted to mention, so what is Nova? I mentioned it once. It's got this other system. All Nova is, and this is really cool, is adding this data availability committee. So otherwise, the diagram is exactly the same. It's just what I explained. But rather than batching and compressing and posting to L1, we instead batch and compress, hand it to a committee, have them generate signatures, and post those signatures to Ethereum, which is how you get so much cost savings when using the Nova chain, but why it has an additional security assumption compared to Ethereum. And then I just wanted to wrap up a little bit by talking about I talked a lot about where we are and sort of what's great about the technology. I want to really talk about sort of where the technology is not yet and what still needs to be done. And this is something that's been sort of a huge effort for us to try to figure out. There's so much going on, there's so much complexity that really sort of keeping people aware of kind of the status of this technology, of where we are, is really important. L2Beat, for anybody familiar, has done an amazing job with this, and I would highly recommend anybody who hasn't to read through their security analysis, which they've done on all the major rollups. But just to talk about kind of where Arbitrum is in this regard. So Arbitrum is, I think, right now, fair to say, the only optimistic rollup in production with fraud proofs, which is incredibly exciting and which we have been since launch, and is really core to us to actually lead tech first. We come from an academic background, the tech is important, but it's not a full rollup yet. And I wouldn't want to consider it that, because for Arbitrum, validation is currently permissioned, which is one of our big priorities for this coming year, is to drop permissioning. Now, it's not just us. There's a great set of validators. I think actually in the coming weeks, we're going to do an announcement where we list all the different entities that are currently validating the Arbitrum chain. But having it be fully permissionless so you can truly make good on the promise of anybody can force it to be correctness is critically important. Next is the sequencer's fast finality guarantees. They're very useful, and in practice, we're running the sequencer now, which is fine as a short-term solution. But these guarantees only hold if you trust that sequencer. And so getting a more distributed system where you can kind of have a much stronger guarantee that the ordering you get quickly will definitely be the ordering you get when those batches are posted on chain is a really important step forward to, again, reaching sort of this real promised future. And the last one, and I think this is sort of the hardest the hardest issue, and I think the biggest sort of discussion, and one that's sort of really important and has been happening a lot here, is how do you think about handling critical bugs in these systems? That fundamentally, this is sort of a really scary process. If Ethereum hits a bug, or Bitcoin hits a bug, they will fork and fix that bug, because it's in the core protocol, and those protocols can fork. But what do rollups do? Rollups are smart contracts. And so figuring out sort of, if Ethereum would fork and fix an issue in Arbitrum, that would be amazing. But I think that's a long way to come, and that's sort of what you get into when you imagine enshrined rollups, which is a whole other conversation. But how to do sort of without that in a way that maximizes decentralization while also protecting ourselves from the risk of bugs, because anybody who's sort of extremely confident they don't have bugs today, I think is overconfident. And sort of figuring out what the balance here between sort of necessary critical emergency paths and security for users is a really important question. And I know, just sort of shout out to one idea that Vitalik's been running with a lot recently. There's some really cool work being done around the ideas of having multiple provers and having a majority of those provers need to all agree. Because then if one of them has a bug, as long as the other one doesn't have the same bug, then they can be checks for each other. And if you have multiple independent implementations, then you get a lot of the same security benefits that client diversity has for Ethereum as for rollup security, which would be a really big thing. So yeah, thank you all for bearing with me through this, and I hope it was interesting. Been a total blast being here, and yeah, I think we should probably have a few minutes for questions.
Thank you so much, Harry. We have time for 3 questions, so could you please raise your hands?
Hey, thanks. This was great. Do you see Optimism's Bedrock and Arbitrum's Nitro converge in the specifications?
So there's absolutely been a lot of kind of very interesting convergence between Arbitrum and Optimism over the years. Both projects, obviously, that have been building for quite a long time. I think that sort of, and this is, I don't think this is happenstance, that like we've learned from each other and kind of design models have shifted. I'd like to say, and take this with a grain of salt because I'm obviously biased, that sort of our initial design was much more influential, particularly interactive fraud proofs, which were a mechanism that we have been kind of arguing for years, and finally won out on, versus the alternative, which was on fraud proofs, which kind of was the original Optimism design. So I think there's a lot of alignment there and a lot of coming together, and I think there's a lot of room for standardization. Yeah.
Hi, Harry. Thanks very much. Just on the last topic you were talking about critical bugs and how you could fix them and the sort of issues that raises, I was thinking about what Danny was talking about in his talk in the opening day, minimizing governance. Do you see any prospect of breaking out the Arbitrum design into multiple components where a bunch of them are immutable and you're able to restrict the governance to just a small part?
No, it's a really great question, and I think it's something that sort of, as we are now kind of in, and I'll say kind of for context, Nitro was our biggest priority for a very long time because it really kind of was solving key performance issues that users were having on the network. I think our next priorities are all around really deep diving on these questions of exactly how much can you minimize. Upgradability is a really tricky thing because a lot of the time, if anything is upgradable, then that component could be captured. And so really figuring out sort of like, if there are ways to sort of modularize your security in a way to create protection is sort of a really interesting open-ended question. So for instance, a modular stack, which is just a set of layers on top of each other, doesn't really help there if some of them aren't upgradable, because if you control an entire layer, chances are you can do whatever you want. So figuring out sort of what arrangements there are to minimize that, I don't have a great answer, but it's a really interesting area for work.
Hey, thanks for the great talk. So asking kind of like a spicy question, what is like the core reason why you are still maintaining a whitelist on the fraud proofs? And then, if that's for like, gas reasons or like DOS reasons or whatever, is there a reason you wouldn't deploy, a version of like Arbitrum on something like Goerli that has, non-whitelisted, fraud prover, so that you can increase kind of the confidence of people by able to generate fraud proofs or at least run that mechanism themselves?
No, it's a great question. No, and I really appreciate when people ask critical questions. I think a lot of times in this space, there's too much trust that's put into teams, and it's really important to be skeptical. So there's a few different reasons. I think kind of both the sort of performance of the rollup protocol as many parties come in, and sort of confidence in sort of the underlying fraud-proof mechanisms, which have been growing over time, are sort of kind of core reasons. I think that in this coming year, and I fully expect within the next 6 months, we will have permissionless fraud proofs on mainnet. As to why not Goerli, it's an interesting question. We totally could. I think the main argument against it is that having the code on testnet and the code on mainnet be exactly the same is the best way to sort of minimize the chances of bugs. We have, if you're interested, a large amount of fuzzing that sort of has been done on the fraud-proof mechanism itself, which is obviously sort of not very visible to users, but there is quite a bit of it. Would be definitely happy to point at that.
Thank you so much, Harry Callender. Please give him a big applause.
Thank you.
Hey, welcome everyone. This is our next talk, The History and Future of Decentralized Operation with Wouter Kampmann. Please give him a big applause.
Okay, seems that the Wi-Fi issues have been resolved, so let's get started. Welcome everyone, I'm Wouter. I will talk to you today about the history and future of decentralized operations at MakerDAO. First, a little bit of background. So for those that are not familiar, MakerDAO is the foundational DeFi project behind the DAI stablecoin. In 2014, this started with Rune Christensen, one of the founders, posting an e-money post on Reddit. And then in the years after that, we launched several products such as a single collateral DAI, which is Maker, but only with Ethereum as collateral. In 2019, there was the launch of multi-collateral DAI, which also added other collateral types. And then after 2019, when Maker was still functioning as a classic foundation, we started to decentralize. And that simply means that we dissolved that foundation and we rebuilt everything in the DAO. So we have had almost 2 years of experience with that now. And yeah, we are wondering what is coming for 2023. Will it be MakerDAO V next? So very quickly, myself, I have a background in software engineering. I joined MakerDAO in November 2017. At the Maker Foundation, I was the head of engineering. And after that, when I also joined the DAO, I became the co-founders of one of the 20 core units, as we call them, the contributor teams at MakerDAO. My core unit is called MakerDAO SES. This is short for Sustainable Ecosystem Scaling. We remove barriers between decentralized workforce, capital, and work. Lately, we have been thinking more and more about decentralized operations. And while you may ask, why don't I just use the term governance as any proper DAO member? Well, decentralized operations, I define it very simply. For me, it's the art of getting things done in an open, transparent, and decentralized organization. And by things, we like to have work that produces actual value, not just activity, but actually creating value. So why the term decentralized operations? Well, DAO governance involves mostly discussion and decision-making. It is not enough to get things done. This decentralized decision-making needs to be supported by effective execution, and decentralized operations includes governance, but it emphasizes the execution part. So we will be talking a lot about voting, we'll be talking a lot about governance stuff, but we say decentralized operations because we realize we need to execute and deliver. So let's return to MakerDAO then. What does operations and governance look like today at MakerDAO? There are a number of well-known concepts that have been implemented basically when the DAO first started for real, so 1 year and 10 months ago. And of course, the foundation of it all is token voting. So Maker has token voting by MKR holders, and it also works with delegates. So MKR holders, they can approve changes to the Maker protocol. They have to approve these changes because the Maker protocol is permissionless. So without a majority of the vote, you will not be able to make any changes in any way. These changes, they can range from simple parameters such as stability fees, debt ceilings, and so on, but also bigger things such as collateral onboarding and offboarding. Today, about 15% of the total MKR supply is delegated, and this is delegated by 222 addresses. We have to say addresses because we don't know how many people are behind those addresses. There are 24 recognized delegates, 92 shadow delegates, and these recognized delegates, they do receive compensation proportional to the voting weight, although there is a limit. So for example, the current payout of the delegates is around 120,000 in cost for the protocol per month. If you're interested in voting our delegates, then definitely have a look at our voting portal, vote.makerdao.com. The second piece of the puzzle today are the Maker Improvement Proposals, the MIPs. So Maker governance follows a monthly governance cadence. The MIPs, they go through 3 phases. First, there is the request for comments. This lasts 3 weeks and 1 week where the proposal is frozen so that the governance participants can properly form an opinion about what is in there. If the RFC proceeds, then there will be a governance poll. Typically, this is about 3 weeks, and yeah, this poll will then be up on the voting portal that you just saw. MKR holders and delegates will then be voting on the individual proposals. Could be that one proposal makes it, another doesn't. All the proposals that make it then are then bundled in the executive vote. So this is one smart contract that bundles all the changes that have been voted in by governance that month. And then, yeah, if MKR holders approve this executive vote, then these changes are applied to the blockchain protocol. The MIP system is quite advanced. For example, we use templates, which we call sub-proposal MIPs. There are hundreds of proposals that have been voted on since early 2022. If you want to know about all the MIPs that went through Maker governance, go to mips.makerdao.com. And the last piece of the puzzle are the contributors, the core units. As you may know, Maker is a pretty big DAO, so we have 20 contributor teams, 100 full-time equivalents of contributors around. These core units, the way that they're voted in, it's with 3 proposal types. So they define or they propose a mandate, they propose a budget, and they propose their facilitator, the person who will be responsible for interfacing between governance and the core unit. So MakerDAO grew quite spectacularly in 2021, and as a result, the total expense has also grown to a total of about 30 million a year. The scalability of the elements that we saw is reached now in 2022 with the bear market that has kicked in. Maker has long been known as the protocol, or one of the few protocols in DeFi that is actually profitable. In the longer run, if you average it out, it's still the case, but if you look at the latest months, that is no longer the case, because the bear market has taken its toll, and you can see that the DAI expenses remain around 30 million. So what are the challenges that we have faced in Maker governance, and what are some ideas that we're thinking about to improve on the current design? The first challenge that I want to talk about is stakeholder alignment and political deadlock. So in a truly open and decentralized organization, it is very difficult to agree on things, even the smallest things, let alone long-term vision and strategy. Maker has been experiencing that firsthand throughout the last 2 years. There has been a lot of governance drama at Maker. You probably read about us, even if you're not following the DAO up close. And at times, core units, the contributors, they really got sucked into this drama, and they broke down entirely in certain cases. So there is an incredible noise factor. There is a lot of distraction. And this culminated a while ago when there was a standoff between 2 factions over a set of MIPs that were about real-world finance. So there was a new core unit that was up for vote to be voted in. And this was the lending oversight core unit. And then there was a Maker Hathaway fund that was up for vote. I won't go into the details of what these proposals were about, but they came to an ultimate standoff between the 2 factions. And as you can see in the screenshot, there was a record MKR voter turnout. And yeah, this attracted quite a bit of attention. And it caused a lot of distraction in the DAO. At that time, definitely, political rhetoric reigned supreme over the rational debate. And one of the reasons is that MakerDAO has very few consensus-building tools, other than just a forum to have a discussion, and then majority voting, which really isn't a consensus-building tool. You do that when you can't reach a consensus. So what might be an idea to improve on this? Recently, there has been a lot of talk about the idea of decentralized voter committees. In fact, this is a main element of the proposal that was put forward called the Endgame Plan by one of the original founders, Rune Christensen. Voter committees, they recognize, on the one hand, the political nature of decentralized organizations, but at the same time, they try to apply some structure, they try to offer some mechanisms to form consensus and to reduce the conflicts that are going on all the time. What it does is, a voter committee is quite simple. It is just a group of MKR holders and delegates. And the important thing is they are self-selecting. So you have people in a group that are of the same mind, they think the same thing about what Maker should do next, what the long-term strategy should be, etc. And of course, not everyone might agree with that group. So there might be multiple voter committees. The idea is that these voter committees will put forward strategies and that the MKR holders can then vote in a liquid election system on the combination of a strategy and the delegate that they believe in. If you think that this is quite similar to political parties or elections, then you're quite right. I don't think it's a coincidence that we are rediscovering the same mechanisms that have been tried and tested. Another part of the voter committee setup is that we want to restrict the flexibility and the possibilities that these voter committees have, because if you leave all possibilities open, then there is a lot larger space for a disagreement. So another part of the design would be a number of fixed scopes, a number of business activities that Maker should focus on and not go outside of that. Maker is not an ice cream factory, for example. The scopes that have been proposed are so far protocol engineering, real-world collateral, permissionless collateral, and growth. This will probably not surprise. The strength of these is that they define the scope and make it closed. And then as a last element, these voter committees, MKR holders and delegates, they need to deal with something else that is challenging about Maker, which is it's a very multidisciplinary organization. And you can't be at the same time an expert in engineering and finance and all the other areas of expertise that are needed in Maker. So when these voter committees, they put forward their strategy, they will define for each one of those scopes how they see the future for Maker. But by doing so, they will be supported by a number of expert councils that have been put forward by the workforce, by the core units. And this is one idea to deal with the difficulties within Maker to reach agreement about the long-term vision and strategy. What is the next challenge? The next challenge is broken transparency and a breakdown of trust. Maker is one of the most radically transparent organizations, not just within the crypto space, but I think globally. An important lesson that we've learned is that transparency in itself is not enough. The right information really needs to be served to the right audiences at the right abstraction level. People don't have time, not everyone has the time to read through long documents and just distill the information that they may need. So standardized structured data needs to be made available via APIs if it is to be analyzed, summarized, and leveraged successfully. Today, this is the case for some types of data in Maker, but not all. So the clearest example of this was the core units and their budgets. All information was always available. It was on the forums, but it was very difficult to find. Our user research has shown that stakeholders were unable to find even the simplest relevant information. Which core units exist? What are they doing? What is their budget? And what are they spending their money on? A result was a breakdown of trust between MKR holders and core units, and even MKR holders and delegates, because people had this impression that despite all the so-called transparency, there was a lot of obfuscation going on. So what is an idea how to deal with this? There's the idea of decentralized operations platform. We want to leverage the power of software to serve the right information to the right audiences and automate processes and embed best practices. This isn't exactly a very original idea, but it is one that will work, we think will work properly for Maker. In fact, we have already been doing this for the core units and the budgets, this piece of information that was so difficult to understand for stakeholders. We created a limited prototype that focuses specifically on that information. So if you go to expenses.makerdao.network, you will see a clear overview of the core units. Right now, this platform is being used for core units to submit their budgets, and core units can use it to verify that they've properly reported on their budget. This information is available on the forum, but if you would want to collect the same information that you have in 5 minutes here, you would probably need 5 days or longer. So what is the next challenge? Coordination failure between core units. There is a construction error at the heart of MakerDAO that we were not really aware of when we put forward the first proposals for the DAO. The mechanism goes like this. So core units are voted in individually by MKR holders and delegates. For example, you may have the growth core unit that is voted in separately than from the smart contracts, or the protocol engineering core unit is voted in separately from the Oracle's core unit, for example. So when coordination is needed between these core units, and if you want to be successful and if you want to deliver value, a lot of coordination is needed. These core units, they can only propose work to other core units, but they can't enforce a collaboration. So there is a constant negotiation that goes on between the core units, how things should be done, what are the priorities, and if core units don't agree, there is no one stepping in and saying, we're doing it this way or that way. In fact, the core units then just walk away and say, okay, you do you, I'll do me, and we'll each just do our job. The result is, because these core units, they have a defined mandate, they have a long-term work stream, but there are no end-to-end deliverables that are defined. So as a result, core units don't feel responsible if coordination fails. So you might have a core unit that, say, builds a front end and does a tremendous job, and then you might have a core unit who needs to promote the front end, but they haven't been aware that it was built or that where it is available, and the marketing might fail. Or you might have disagreements between, for example, technical core units, which architectures to use, and if they don't agree on that, well, the end result will simply not work. So a lot of work is done. It's just that sometimes not a lot of value is created because the pieces aren't integrated or working together well. So which idea can help with that? We have been talking a lot about project-based budgeting at MakerDAO, and believe that this will be a much better structure to deal with this. So real value is really only produced when delivering an integrated solution. Delegates and MKR holders, they should approve these integrated solutions, projects, more so than mandates. So they wouldn't be paying for work, like for coming to work every day, but they would be paying for the actual results. Now, the party proposing the solution, so proposing the project, they should be responsible, and this is critical, for the end-to-end delivery. Not just the technical part, not just the marketing, not just the front end, not just the back end, the integrated solution, because that's how you create value. And then responsibility comes with authority over the full project budget. So if core units disagree how to implement a certain piece of work, then the party proposing the project should have the authority to say, well, we'll go with your solution and not yours. The current system that we have with MIP 40, which defines the budget of core units, and the MIP 39 with their mandate, it will probably not go away, but we will gradually try and transition it towards a system that is more balanced. As you can see in the diagram, you can think of today's budgets as 100% retention budgets. We're just paying you to do work for the DAO. Instead, we would be transitioning to a budget that is split up between still a partially retention budget, but separate from that, clear project budgets where the cost items are directly related to the integrated and valuable work that is delivered. Then for the last challenge, talent acquisition, onboarding, and the compensation question. Maker has been struggling a lot consistently with hiring, onboarding, and comp challenges. MakerDAO SES, my core unit, we have run an incubation program for some time, but now we are winding that down. Why? Well, it's very difficult and time-intensive to coach teams throughout the long and costly onboarding period. I already mentioned when you make a governance proposal, it takes you all in all 2 months to go from the RFC to the final vote. But if you really want to propose a core unit, you need a lot more work than that. At least 2 months of preparation adds up to a total of 4. It's difficult for people to just do that out of their own effort without compensation. However, for a core unit, it's also very difficult to make these calls. So we have been doing that for a while, but we felt that the model really wasn't suited for the new situation that we're in. And of course, a large element of that is simply the bear market. This has ended the onboarding of new startup teams, and it also has created a lot more discussion about where the money should go. It's easy to get a budget approved if there is enough budget to do everything. Comp questions in general, they're extremely difficult in a global, open, and decentralized organization with such diverse areas of expertise. Even if you know how much an engineer is worth or how much a web designer is worth, you may not know how much you should be paying for a risk analyst or someone working in banking, for example. So we have attempted to ameliorate that by hiring, or incubating rather, a people core unit, but this proved to be extremely difficult and has not succeeded so far. So what is the idea here? The idea is to make Maker Academy instead of an incubation program. A Maker Academy would be a platform that is open to everyone and that is also permissionless, meaning that it is out there in the open in the DAO, and if you want to create a core unit or you have an idea for a project that you want to see funded, you need to know how do I fulfill the role of being a good core unit facilitator? What are my responsibilities? How do I need to interact with governance? And all these things, they can be made available in open platforms, open education platforms with specific courses, but also general topics. Especially today, when Maker is going through a lot of transition, there is a lot of complexity on the technical side, there is a lot of complexity on the real-world finance side, there is a lot of complexity on the organizational side, and there is a lot of complexity in the new proposals that are up for vote. So yeah, an open and available platform for education and training may help people to acquire the skills they need. And then if you combine it with the possibility of grants, then you get a funding mechanism that doesn't need to be inside a single core unit, but that can be done out in the open. And so Maker can continue to onboard the talent that it needs. So these were my 4 challenges. So what does the future of decentralized operations at Maker look like? No one knows. There are a lot of ideas that are floating around. We do believe that the solutions we're thinking about, the solutions we're building, they're all open source software, and they could be interesting for other projects as well. So yeah, thank you for coming to my talk, and let's continue the discussion.
Thank you so much, Walter Kampmann from MakerDAO. We don't have time for questions, so feel free to reach out to Walter outside, and we're having a lunch stop, so join again at 1:30. Thank you.
Hello, everyone. Well, today we have Will Villanueva. He is a former ETH2 co-researcher. Will also is currently the CEO and co-founder of Elemental Finance. Will, welcome.
Hello? Okay, cool. Hey, what's up, everyone? Give me 1 second to get set up here. Get my water. All right. I don't think this is working. Oh, there we go. Cool. All right, so today I'm going to be talking about LP, volatility harvesting across yield rates. So Element Finance, we had an event last night. If any of you were there, thank you for coming. So it was super cool, super enjoyable. I'll go into what we do in a second, but one of the major things, or one of the things that I want to talk about is what is volatility harvesting. So volatility harvesting at its essence, if you think of AMMs in the current market, are sort of volatility harvesting engines. And what does this mean is as spot prices drop or as spot prices rise in the space, this gives opportunity for market makers to then go ahead and arb the market, make profit, bringing those spot prices to a certain level, and allows LPs to capture fees and get value from those volatility changes. So this is essentially, what I think of when I think of a volatility harvesting tool. So let's apply this to the yield markets. Before we do that, let me give you a quick intro into what does Element Finance do. So Element Finance, at its core, is a yield splitting protocol. So what we do is we take different yield sources in the space. Let's say you have an ST-ETH position. Let's say it's a Yearn position. A lot of our things are built on Yearn. And what we do is if you put $1 million in, we take that position, we split it into 2 parts. So there's the principal and the interest. So you have a 1-year lockup. If you have 10% interest on this position, you have $1 million in principal. And I guess this shows 20%. So 20% on $1 million would be 200K in interest. So at the end of the term, at the end of the year, you can collect both of those. We use a curve. This was developed mainly by actually Yield Space. We did an alteration on this curve. It's called a constant power sum. And essentially what we do is during the market, we let people essentially stake the principal that they have that's locked up. And what the curve does is it's a time-based curve, and it sort of follows this concept, where I give you $1 for 99 cents or 90 cents. So this is the concept of the opportunity cost of money. So if I say, hey, I'm going to offer you, this $1 million, but you can't touch it for a year. You can't do anything with it. What is it worth for you to have that $1 million? I can't put it in a savings account. I can't stake it. I can't farm with it. I'm losing some type of interest on that, right? So I say, hey, I think I could probably get like 15% APY. I'll give you 90% of that. So here's $1. You can't use it for the next year. I'll give you 90 cents for that $1. And so what this curve essentially does is it acts with respect to this time period between the constant product and the constant sum formula. So early on, it has price discovery. You can have the APY change on the principal, this $1 million that's locked up. And later on, it sort of converges one-to-one value. If I say, hey, here's $1 million tomorrow, you can't use it until tomorrow, you'll probably buy it for $1 million, right? Versus for a year from now, then you get that opportunity cost. So this is essentially how that works. So what we saw early on in our platform is these markets actually worked really well. As people locked up their principal in the AMMs, people were actually trading these with the opportunity cost of money based on the variable rates that you could see in the market. So, for example, when we had first launched, we saw a curve try crypto term where the yield was, the fixed APY was at 15%, and the variable rate was at 9% in this term. So what ended up happening is the fixed rate, people actually brought the fixed APY to be higher than the variable APY. How does that make sense? It's hard to grasp that, it's hard to understand that. What happened is we were in a market lull. So the variable rates had all dropped in the space, and people were speculating that they would rise. And sure enough, they did. They ended up making money off of it. And so why is that related to the number value here? So we have this system called yield token compounding, which essentially lets you go through and leverage your exposure to variable interest. You go long on variable interest. And it's this concept where you mint these principal, these yield tokens. You sell your principal for a fixed APY percentage. And you do this repeatedly until you own a stronger exposure to the yield. So this is like, I don't want to go into too much depth here, but if the variable APY is at 20%, and let's say the fixed APY is at 10%, I have a 10% spread. If I basically rehypothecate and do this, I deposit, I sell, I deposit, I sell, I deposit, I sell. If I do this 6 or 7 times, you know, I can 7x that to around 70%. So this causes an upward price action in the fixed rates in the market. And so if I believe the variable rates are going to go significantly higher, I might be willing to let the fixed rate go higher than what the current variable rates are. So we saw some other interesting volatility behaviors. At one point, there was, I actually did a talk about this at another conference. There was issues with MIM. I think a lot of you remember that. There's a whole scandal there. We have a lot of those sometimes in our industry. And the fixed APR, like, you know, popped up to 130%. And then we had another case where we had a WBTC vault where it dropped completely to 0%, actually. And during this time, we saw a lot of volatility movement. The price action, basically the fixed APYs went up and down. They went to 50%, to 100, down to 20, back up to 70. It moved all around the place. And so this is sort of, you know, an example of the volatility in action. Eventually it normalized to around 10%. So what do we notice in the fixed rate market is it generally sometimes, except for some of these exceptions, it tends to follow the variable rate. Ends up being somewhat similar, the APY, to what the variable rate is in the market, sometimes a little less, sometimes a little bit higher. They tend to track each other, they're correlated. This is what we've seen from the data that we've gotten in our current V1. And this is where, you know, I've done a talk on this before, is essentially these fixed rate markets that we do, they're not really just fixed rate markets, they're yield markets. We're essentially creating this value capture mechanism for yield markets. And so what is like element finance, like, and these systems and fixed rate systems as a whole? You can sort of see them as it's more than a fixed rate system. It's a highly liquid arbitrage market that lets you sort of play and create profit as yields shift within the space. So as yields spike to 10, they drop to 2, I can create profit off of this in a similar way that if ETH spikes up and then drops, I can create profit mechanisms off of this. It also allows for really cool things like leverage, going long variable, being, you know, negative on the, you know, future variable interest. Like I believe this one's going to go to 0%. This farm shot up in value. So sort of the dream for me, and it's not just element, it's sort of the fixed rate space, which is akin to, you know, some similarities to zero coupon bonds, other things like that, is that it ends up becoming this intermediating layer for yields across lending and borrowing platforms, and also like not just lending and borrowing platforms, but yield platforms as a whole. So real quick, I'm gonna go into like one example. This is gonna be, I can't go into a lot of the depth, but I wanna sort of paint a picture. So I did a Twitter thread, you can check it out on Twitter, it's pinned, where I actually coded, I went for a week in my room and coded a bunch of simulations. And this simulation particularly was on something called Fiat DAO. And what they did, it was akin to Maker, where they had a 1% stability set fee. And that 1% stability fee is basically your borrow rate, right? And what they did is they took principal tokens as collateral. So I could take a principal or a fixed rate. These principal tokens are these fixed rate tokens, right? So I could buy a fixed rate, use as collateral, borrow fiat, swap that to DAI, buy more fixed rate DAI. I could basically leverage into the fixed rate side. And so if the borrow is at 1% APY, or let's say Maker's stability, if you want to think in relation to Maker or other systems, is at 1% APY. Essentially what we're able to do is if the fixed rate's at 3%, you can leverage into that fixed rate until it basically converges to that 1% value, which is really cool. And what does this also allow for? So there's this concept of fixed rate borrowing mechanism or adapter. There's a few people who are working on this on the Element platform actually currently. And essentially what this is you could take these instruments that we have and you can plug them into Compound and Aave and existing systems. And what you do is you essentially create a hedge market. You transform them into fixed rate borrow markets. So let's say I have a Compound borrow position. Let's say I'm borrowing DAI from Compound. Let's say we hit very low utility rate. And in this case, the APY to borrow goes low. Let's say it goes to 0.5%. This is great. I want to lock that in, So what you can do with sort of the system that, we have is you take out that borrow and you hedge by going directly into the yield. So these are the yield tokens I talked about earlier. And what you do is, let's say, in this case, I'm saying, okay, lending is at 3%, whatever, borrow is at 1% APY. If suddenly the borrow goes up to 10% APY, the lending side also is going to spike up to around 10% or 12%. And so because I hedged my borrow position with this yield exposure on the lending position, that means my borrow position gets pretty stable. I'm hedged against stark drops or rises in the interest rate. This is really cool because we can basically turn it in any platform, lending platform, doesn't matter what chain, into a fixed rate borrow system. This can be built on top. This can be an adapter. So what does this mean is if you sort of take a step back, you can see that these mechanisms, these fixed rate and variable rate and these yield markets that we have, what they do is they create this convergence layer for DeFi rates, for lending market rates. You use it to take out borrow positions. You can create essentially fixed rate and variable positions on the lending side, the side where you get APY. And when you go cross-platform, if I basically do a fixed rate borrow on platform A, and then I essentially use that to sort of go into and purchase the principal tokens on platform B that are certain value, you end up having this sort of liquid layer in between that brings all those rates to convergence and brings them together. It's really cool. I wish I had a better diagram for this, but I'm sort of starting to introduce this topic and playing with this. And this works across different L2s, L1s. It's really, really powerful, actually. And so we've already started batching basically activities on Aztec for Ethereum. And so what I sort of see is this world where we can sort of batch a lot of the activities from different layers, different chains, all on one chain. And you can sort of interact and arbitrage basically the borrow, the lending rates, the yield rates within that one chain. That sort of works as this centerpiece for everything. So I want to talk for a second about AMMs. So AMMs, I think, there's a lot of downsides to them. So we had Uni v3 with concentrated liquidity model. You can kind of see AMMs also are sort of a free straddle option for market makers. A lot of the value that's captured off AMMs goes to market makers, not to the people providing the liquidity, not to the LPers in an organic way. This is why a lot of people are doing research on cool ways, how do you bring MEV into the actual AMM? How do you bring transaction ordering and validator activities into the actual AMM? Because sort of the most altruistic position in the markets is being an LP, especially in an organic market where you don't have emissions, things like that. And they take on a lot of risk. So spot prices can, go up, down, through the roof. They a lot of times can see less gains than if they had held one position, or worse gains on the other spectrum. And so there's definitely work that needs to be done on AMMs, but they're really, really good for yield prices and yield tokens and principal tokens and everything that's involved there. And the reason why is because if I have fixed rate USDC, and we call these principal tokens in our platform, and that's at 10% APY over a year, that means it's going for 90 cents. Day by day, that 90-cent value converges to $1. You don't really experience any impermanent loss. It's sort of more like a stable swap. The fees are pretty cool as a percentage of that yield that people secure and swap with. And that's really interesting. And so one of the issues we've had in V1 and what we've been doing is we have this liquidity fragmentation. It's like I have this 6-month term, this fixed rate term that I'm interested in, but it's 3 months through, and now I need to switch to another 6-month term, or as an LP, it makes sense for me to pull out my position and go into another one. These are some of the weaknesses. So we did a bunch of simulations and analysis in our current fee markets, capturing volatility in the space, which is super interesting. This is fairly complex. The main thing that I'll share, the biggest learnings, is as you see yields rise, that is one of the highest value capture mechanisms for LPs. As you see a yield rate drop, this is actually also, if you're active, extremely profitable. So what happens if a yield rate drops? So in this case, we have a situation where we're going from 10% to 2.5% APY. And in 2.5 months, it drops to 2.5% APY. And this is a 6-month term. So that drop essentially brings that principal token, right? If 90 cents on a dollar would be 10%, if it drops to 5%, then that's 95 cents on a dollar, right? 5-cent discount. So essentially, it's worth more. And what you can do as it drops is you just sell the principal token. So someone who locked in a 10% fixed rate APY, in 2.5 months, when it dropped to 2.5%, they sell the principal tokens. They got 4.2% return in 2.5 months because they sold it, which equates to 20% APR. So if you're going into a position and you see, I believe this rate's gonna drop, it makes sense to buy the fixed rate side, because once the rate drops, then you can flip that, you can sell that. And then you can basically get an early redemption on your APY. You get fulfilled quicker. On the other case, if the APY rises, you get a higher exposure to the fixed rate APY. So you get more yield exposure. It's also a profitable endeavor and mechanism. And so what does this lead to? This sort of leads to products that can be built on top, active strategies, vaults, really interesting things, even bots that market makers can do to really capture a lot of this value. The value is absurd that can be caught, especially once you're doing borrowing lending markets, once you're hedging on those, once you have principal tokens as collateral, once you have these markets running truly smoothly. There's a lot of ways to sort of make profit off of changing yield rates. So it's fascinating. This is just for fun. So another thing we saw is it's sort of unideal for an LP, because with these terms we used to have, where essentially in Element we have usually 6-month terms, and we do a new 6-month term. But what happens is here's a simulation, the fees drop off as this term ends. It doesn't really make sense for me as an LP to stay the full term. It makes more sense for me to pull out. Why do the fees drop out? Because as time goes on, the value converges, so you have less of a differential, so the fees are less, and also people are less likely to trade on 1 month left left of APY. So Johnny Ray, my co-founder, we're both ETH2 researchers, but he actually recently came up with a new model. We're calling this hyperdrive. And it introduces no more terms, LPs as perpetual positions. And essentially this new AMM that we've been researching, and we'll be releasing a lot of data on this, simulations on it here soon, lets you basically underwrite someone to take out a fixed rate term on whatever time they want. So they can say 6 months, 3 months, and it's a brand new term. You don't have to worry about these terms going halfway into a term. I have 1 month left. You underwrite that position immediately. And this is really good for LPs too. This is really good for users. If I want to take out a loan from Aave, I want a 1 month, 3 month, 6 month. I don't want this weird halfway position thing. For an LP, it's a perpetual position. I get average exposure to basically all these different term lengths. It's a really good situation for them. They're able to capture and garner more fees. And this also allows for just better systems to be built on top, simplicity, and better vaults, better value capture mechanisms, better ways to go long on variable yield on the market, better ways to be negative on variable yield, and sort of play with these markets and have fun. So this is LP volatility harvesting cross yield rates. I'll try and release a lot more simulations and data here soon on Twitter. Follow us. This is really cool. We are doing some like new and groundbreaking research here, and there's a lot of profit mechanisms. So like, pay attention is all I have to say. Thank you.
Thank you, Will. We have a little minute for some Q&A. Anybody have a question?
Any questions? Yes, Matthias. Soon. DM me. No, just DM me, yeah. Any other questions?
Okay, so earlier this year, there was a project called Defraud Finance on Avalanche, and they did leveraged yield farming. But they had a lot of trouble with keeping the liquidity in order to do that. So in your example where you had that 3 to 7 leverage on the dies, how do you maintain that liquidity to keep that so people actually want to trade the other side on you?
Yeah, so great question. So we actually saw like, I think it was through the bull market, something like $400 million of trades on our platform. So we actually saw a really active activity on yield token compounding or increasing your exposure on the variable side. I think maybe some of your question is, how do you match that if you have leverage to the other side, because that's sell? How do you match that on the purchase side? That's why things like having these fixed rates as collateral, right? Being able to leverage into buying the fixed rates is important. Liquidity is another thing. Like liquidity's down significantly in the market, including our platform. I sort of think we build sustainable, strong products, things like Hyperdrive, that make sense, that are a significant leap on what exists in existing TradFi. Like this stuff doesn't exist. It's crazy cool. And I think it's just a matter of time of sort of building and garnering that space. I've been looking at a lot of things too, looking at real world assets, like some other things that can also play in as yield sources. I think staking derivatives are really good yield sources. People are gonna do those regardless. MEV is an interesting one, et cetera, et cetera. So yeah, any other questions?
No more questions. So thank you, Will.
Cool, thank you.
Bueno, remember, closing ceremony will be at 3:30 p.m. at top of the mountain. Thank you. Well, now we have Arya Klagsman and Daniel Perez to talk about security risks in DeFi. Please welcome.
All right, let's see. Hi everyone, and thanks a lot for coming to our talk. So I'm Daniel, and with me here is Ari, and this is a project that has been done by a few people. So there's Sam and Luis who are in the audience, but won't be presenting here today. And so today we're going to talk about security risk in DeFi, and in particular we're going to try to sort of give some definitions and explain how technical security and economic security are different, or how they differ. So a quick outline of what we'll be presenting today. So this talk is meant to be fairly accessible, so we'll start by presenting a bit the different primitives used in DeFi, and then we'll present a couple of protocols that are that can be built. And once we've done this, we'll enter a bit more into the main part of the talk, which will be explaining what technical security and economic security is. And we will finally present a few open challenges for research with a focus on these different types of security. So we'll start on a very high level, but what is DeFi? So we have a couple definitions and properties for DeFi. So the definition that we give is a peer-to-peer powered financial system. And for it to be called DeFi, we're saying that it should have a few idealized properties. First one being non-custodial, which means that participants should have control over their funds at any point in time. And next one is that it should be permissionless. Anyone should be able to participate in these financial activities without restrictions or without being able to be censored by a third party. It should be openly auditable, which means that anyone can look at the state of the blockchain or what is powering the DeFi, and be able to see the transactions and what is going on. And finally, it should be composable, which means that different protocols should be able to communicate with each other and to interact to form sort of new financial systems on top of this. So, well, with this DeFi coming, there has been a lot of controversy and all, and we can see this a bit as like two sort of very point of views, an optimistic and a pessimistic point of view, where for the DeFi optimist, DeFi is a huge technological advance. It's a new financial system that's openly auditable and that has all the properties listed before, and that's obviously very promising for the future. And there has been already a lot of good things with DeFi. For example, stable coins like DAI has been used in countries like Argentina to fight inflation and this sort of things. And also we have seen that more custodial system has tended to fail in some places where decentralized finance could have allowed people to have more visibility on what was going on. On the other hand, there's also this pessimistic view that is that, well, DeFi, it's unregulated, it's hack-prone, it can allow people, through its pseudonymous nature, to commit many sorts of crime, like scamming, money laundering, and so on. And, well, there has also been, like, many hacks, as probably you have all seen, and this North Korean hackers hacking protocols, and also a bit more recently, the crypto mixer being sanctioned, and so on. So, well, in this talk, well, we'll focus mostly on security, which is something that we think is absolutely it's a complete must for the vision of the DeFi optimist to be fulfilled. And really what we'll be trying to do is to differentiate between what is a technical security problem and what is an economical security problem. Before this, we'll give a bit of background around like different primitives that are needed for all this. And we'll start with some very basic assumptions here is, well, all DeFi protocols rely on an underlying blockchain, and it assumes some security properties, which are consistency, integrity, and availability. And there cannot be any DeFi without these to begin with. Then it chooses a few other properties of the blockchain, and here one that I want to highlight because there's a lot of sort of security issues because of this, or like many potential, let's say. It's atomicity, which means that if a transaction starts, it will either succeed completely or it will revert, but there cannot be a half transactions. That just cannot be. And obviously DeFi relies on smart contracts, which are programs that run on the blockchain. And using these primitives, there are a few really essential pieces of software and of other primitives that are required for DeFi. First one being oracles. So because blockchain cannot have access to off-chain information, somebody needs to take this off-chain information and put it on-chain. And these are called oracles and are used, for example, to get price of, say, USD, because this is not information you could possibly have. Then there is governance, which is used typically to upgrade DeFi protocols with time, change parameters, and this sort of things. Then we have keepers, which are off-chain sort of bots, and that will submit transactions to update state. This is because in most blockchain systems, you need a transaction to be able to perform any sort of state transition, and therefore somebody has to take care of this. And finally, there are many market mechanisms that are used in DeFi. There are collateralization, where people will put some money at stake to make sure that he cannot default on the position, for example. Then there's arbitrageurs. There are also liquidations, liquidations which are used if somebody does not have enough collateral for whatever position. So that covers roughly the main primitives that we'll need in DeFi protocols. And now I'll present just a couple of DeFi protocols. Probably most of you are already familiar with these, but just to highlight a few properties so that we can kind of all be on the same page to start talking a bit more about security aspects. So there are many types of protocols, but we don't really have time to go through all of them. So we'll first start with automated market makers, which are decentralized on-chain decentralized exchanges, because on-chain it's way too expensive to have some order book-based dexes. AMMs or somehow has become extremely popular, and they have a lot of good properties, a few properties that are less good. But the main idea is that people will come and provide liquidity to a pool that consists of typically 2 or more assets. And by providing this liquidity, they in some way commit to a portfolio of these underlying assets, and a portfolio that will be rebalanced by arbitrageurs that will try to keep the prices consistent with some other off-chain, for example, prices or prices on some other exchanges. Once that is done, people can trade through this pool, and that generates fees for the pool. And typically, this is profitable in the case where they are volatility harvesting. When that was talked just before was a lot more advanced in this, but basically, if the price is around some line and going up and down, it's typically profitable, as opposed to if the price is consistently diverging, then maybe not so. And there's still some risk, and especially strategy risk and adverse selection risk involved with these AMMs. And another very important type of protocol for DeFi are a protocol for low-level funds, also called lending protocols, which are on-chain markets where people can borrow and lend assets. So typically, people will come and deposit some assets that are pooled in smart contracts. Other people can come and borrow these assets, and to do so, they will need to be over-collateralized, so they cannot default on their position. And an interesting thing is that there are algorithmic interest rates, and which means that typically with these markets, there is no duration risk. And if a borrower would default on his position, which means his collateral ratio is not high enough anymore, he can get liquidated based on rules that are imposed by the protocol. And a final point that's also very sort of typical to DeFi are flash loans. That's quite an interesting primitive because it allows people to borrow money without having any collateral, and the condition for this is that they repay this loan in a single transaction. And this works mostly because of the primitive I described before, which is atomicity. So with all this, then these protocols can communicate together, as I mentioned earlier. And for example, one person could deposit some money in an AMM and get some LP shares, and use these MP shares, for example, in lending protocol as collateral to be able to borrow some other type of asset. And that's a very interesting thing with DeFi, that all this protocol can really very easily communicate. So now that I'm done with this sort of intro background about DeFi itself, we'll dive a bit more into the security. And we'll really try now to delineate technical and economical security. And first, we'll start with some informal definition. And so we say here that for protocol or smart contract to be technically secure, it needs to be secure from an attacker who is limited to atomic actions. And where, like here, being secure has been cannot get exploited. We have a more formal definition of exploit in a paper that we'll show at the end. But for example, it could be not to be able to steal assets. And so here, atomic actions means that the action would be either a single transaction or either a bundle of transactions, but the property needs to be that all these actions will be executed atomically. And because of this, so attacks on technical security are risk-free because basically the attacker can just perform the attack, and at the end of the transaction or of this atomic operation, he can see if yes or no he made money, and if he did not make any money, if he made money, he profits. If he didn't, he'll only pay the gas fees and can reverse the transactions. So by definition, or by kind of extending the definition, a technical attack will always be risk-free. Otherwise, it will fit our other type of attack. And there are some examples of technical attacks are atomic MEV, sandwich attacks, and for example, like reentrancy, or also attacks that exploit logical bugs. And that's all now fairly well studied. We know more or less how to protect against these. There are, of course, like testing smart contracts very well, and program analysis, or formal methods. And these are, in general, the better studied ones. So for smart contract vulnerabilities, we have reentrancy, integer manipulation, logical bugs, all of which are by now quite well studied. There are single transaction sandwich attacks, which is where if a protocol, say, would use the spot price of an AMM to use as a price in their protocol, an attacker could come and imbalance this AMM so that when the protocol would try to look up the price, it would get the wrong price, and an attacker could fairly easily exploit this to make money. Or governance attack, if it's possible in one transaction to do some governance action, an attacker could come, probably borrow enough governance token to do so, and execute some malicious proposal. Lastly, there are transaction ordering attacks, so variable displacement attacks, where an attacker could front-run some particular transaction to make profit instead of the person who initially initiated this transaction. And also multi-transaction sandwich attacks, which are an attack where an attacker could come and see that somebody is trying to swap, but have, for example, a very high slippage tolerance, and he could imbalance the pool before to give the victim a bad price, and then rebalance the pool after, and would get the profit that the victim lost because of the price he got. So now I'll give it to Ari so that he can talk about economic security.
So the other type of security, we define a protocol is economically secure if it's not profitable for an attacker who can perform non-atomic actions to manipulate the protocol into unintended states where they can essentially extract assets from the protocol or cause other sort of mayhem in the protocol. And so economic security is about where you have an exploiting agent who's trying to manipulate some sort of incentive structure of the protocol to profit, like by stealing assets. And since these are non-atomic, they have upfront tangible costs and are not risk-free. Basically, you have to like set up the attack and then actually perform the attack later on, and something could happen in between those two times. And basically, the attack could fail if something happens in between those two actions, and such as the market responding or other agents responding. And to address this, we really need to have economic models of what's happening in between these transactions, and the attacker would need to understand this and basically manipulate what's happening in between these transactions. So let's hammer down a little bit further what the difference is between technical and economic security. So in a technical exploit, we have an attacker who's effectively finding a sequence of contract calls that leads to a profit. And these are either in a single transaction or a bundle of transactions, but it's being done all at once or not at all. And for these, formal models of contracts are basically enough, so to say, although it can still be quite a hard computer science problem to work out sort of the optimal ways for attacks to be performed. In comparison, in an economic exploit, an attacker is performing multiple actions kind of at different times or really different points in the sequence. And they don't necessarily control what happens between those actions. And so there's no guarantee that the final action is profitable. So there's kind of a setup. There's actually performing the attack later. But in between, some sort of market can respond or other agents can respond. And so the attacker doesn't really know if it's profitable at the end. And for this, we need models of what's going on in between, which is a bit different than just formally verifying contracts. And so this is kind of an open area of research, especially around kind of understanding liquidity of markets. So let's hammer down even a little bit further with like a very simple example of something that'll be a technical exploit and then something we can change a little bit about it that turns it into instead an economic exploit. So in the example of a technical exploit, let's say a protocol uses an instantaneous AMM price as an oracle, and that then an attacker performs an atomic sandwich attack to steal assets from that protocol. Because this can be done atomically, this is a technical exploit, but we could change it. We could use a smarter choice of oracle so that this isn't possible, and that leads to instead it being an economic exploit. So here, consider that the protocol instead uses a little bit smarter choice of oracle, a time-weighted average AMM price, but these can still be manipulated over time, but it involves risk for the attacker, but they still may be able to steal assets. And actually, something like that just happened very recently in Mango, I believe. So we can see this also like in data about what's been happening in different protocols. So one example here to kind of illustrate this a little further is something that happened in Compound in November 2020. Now, this wasn't really clearly an exploit, but it kind of illustrates what could have been an exploit and what can be exploits in other protocols. So basically, the price of DAI was trading on Coinbase, and for a very short period of time, the price pumped to $1.30. And because Compound was using Coinbase as an oracle, this allowed a lot of liquidations to be possible on Compound. And that cost a lot of LPs money in Compound and opened up a lot of opportunity for profit from liquidating those positions. Now, this wasn't clearly an exploit, but you could imagine that somebody might set this up intentionally, manipulate this market that manipulates the oracle price, and then profiting from the resulting liquidations. And that's essentially what we've seen later as well. So in a clear exploit, something similar happened in Venus in May 2021, where the Venus market was manipulated, and essentially the attacker was able to leave the protocol with a lot of bad debt. And again, just recently, something similar happened also in Mango. So what are the tools available to like help to fix economic security and make protocols more secure? One of the first ones, the biggest, is really over-collateralization. And here, this doesn't come without risks, though. And so it's very important to include an analysis of the actual economics in designing and calibrating your protocol. So for instance, you could have persistent negative shocks that affect collateral prices, and you could also have kind of illiquid markets around those assets. And this can lead to loans being under-collateralized and the system being left with bad debt. It can also lead to situations where it's unprofitable for liquidators to actually initiate the liquidations, which then also can lead to the protocol having bad debt because the liquidations don't happen in time. And there's also sort of issues that can happen with stablecoins and deleveraging of these stablecoins, like we saw in DAI on Black Thursday, where you had this like short squeeze effect, and you also had this sort of like collapse of the liquidation engine. Some other things that you need to be aware of when you're designing protocols with respect to economic security is the miner extractable value that you can be setting up. I won't go too in depth here because there have been a lot of great talks already about miner extractable value. I'll just point out that DeFi applications tend to give many new sources of MEV, and you need to be considering these. And this is essentially coming from arbitrage opportunities. So for instance, in DEXs, you can have sort of like stale order quotes, and whoever fulfill those is able to do an arbitrage loop and profit. And in lending protocols, there's usually a liquidation incentive, and if you're the person who can come in and perform the liquidation when it's allowed, then you can profit from being the person who does that. And this can lead to consensus layer risks if this MEV is greater than the block reward. Another important area is in the design of governance and the risks that can come up from your governance layer. So the governance is basically introducing a way to upgrade protocols. And these need sort of careful guardrails and careful design so that your governors aren't going to have misincentives to do things that are actually bad for protocol users. And so commonly, governance may not really be incentive compatible with the actual users of the protocol. And this can be an issue. They may not act in the interest of these protocol users. And to illustrate a little bit, in some sense, governors have some honest cash flows. But these cash flows may not always be very high. Sometimes they can crash. And then if they do crash, the region of incentive compatibility might shrink, and it may be more profitable for these governors to, instead of doing sort of honest actions and upgrading the protocol in good ways, to instead decide to attack the protocol and basically steal assets from the protocol or do other things that put protocol assets at risk. And the costs to do this can sometimes be very low in DeFi and should be part of the design of governance systems. So for instance, tokens can be borrowed, and agents can be pseudo-anonymous, and this can lead to low costs to actually do these governance attacks. The last one I want to hammer down a little bit on is this, what we were talking about in the examples of where you have markets or oracle manipulations that can directly affect your protocol. So here we need to distinguish between, one, a market price that is being manipulated, but correctly supplied by an oracle, and two, an oracle that is itself being manipulated. So in market manipulation, you have an adversary who is manipulating the market price, either on or off chain, depending where that market is occurring, over some period of time, and they can profit if they can. If the manipulation, they can exploit it in a protocol that uses that market as an oracle. And these problems persist even if the oracle is not an instantaneous AMM, because it's just, there is some liquidity in the market. Depending on that liquidity, there's some cost to affect the market price, and you can instigate changes to market price that are then reported through the oracle system. And importantly, though, this is risky because you have to do it over time. It can't be atomic, which is, again, the main point about economic security. And this compares to oracle manipulation, where it depends on the design of your oracle, but even if the market price is not being affected, the oracle might be reporting incorrect prices. So centralized oracles have potentially a single point of failure, and you might want to control for that in designing your protocol. And on-chain AMM-based oracles, as we've seen, can be manipulated. And so the costs of manipulating that, depending on the liquidity in those markets, is something you should be carefully considering. And other decentralized oracle solutions are really imperfect for the issue that you can't really verify the correctness of prices on-chain. And so it's quite an open problem how to do this very well. So that sort of concludes our discussion of technical and economic security, but it leads to a host of new research challenges that are really going to be important for securing DeFi protocols into the future. So I'll give you just like a quick flavor of these. One is around composability risks. Mostly these are not very well quantified, but a lot of program analysis can be done to understand these risks a bit better, and then to design your protocols in ways where how you're composing with other protocols is as safe as possible. Another is what we were just talking about, this governance sort of risk, and modeling the incentive compatibility of governors, and sort of modeling out what we call governance extractable value, and trying to understand when are governors in your system incentivized to do things that are good for the protocol, and how do you stop them from doing bad things? And these need economic models about how these governance systems work over time and how the agents make decisions. Another is around oracles. Basically, a similar sort of role as governance, incentive compatibility to report correct prices. And then in a fair amount of work to be done in MEV. And there's just one illustration of sort of like what makes MEV very hard is that if you're looking at just intra-block MEV, atomic MEV, this becomes an optimization problem that resembles knapsack, but where the items in the knapsack can change depending on the current selection. So it should be even harder than knapsack, and so it should be an NP-hard problem. And this becomes even harder than if you're looking at inter-block MEV, and this includes cross-chain MEV, because now you have to look at an intertemporal version of that same optimization problem. And there's also a lot of work to be done in sort of making anonymous DeFi protocols and preserving privacy. So that brings us to the end of the talk. Just as a quick recap, we've covered how DeFi has several innovations, but it also has several risks. And to fulfill the vision of the DeFi optimist, we really need to make sure that DeFi is secure. And to do that, we've delineated two types of security risk between technical and economic security. And the key distinctions that allow this to be useful are that it's based on atomicity, and it really tells you a lot about the models you need to understand security in your DeFi protocol, and the types of models that we, as researchers, need to build out. So thank you, and let's open it up for questions if we have time.
We have time just for one question. So anyone?
No. Just while we're waiting for the mic, so this is based on the papers that we wrote, and this is a QR code in the link if you want to have a look, and there are more formal definitions in there, so please feel free to take a look.
So how does this overlap with a lot of what Gyroscope is doing and sort of your mission and vision? I'm super curious about that, yeah.
That's a great question. So how we've designed, so Gyroscope, we're working on a new stablecoin project where we're building a bunch of different primitives that allow what we think is a more resilient stablecoin design. And it's really coming out of all of the research we've been doing. We've set up some of the initial models that help to understand, for instance, economic security. And the mechanism design that went into Gyroscope takes all of that knowledge into consideration and tries to do the best mechanism design that we can, considering how we understand economic security today.
Thank you so much. Remember, the venue will be open this weekend, so come and talk with the people, with everyone, close deals, etc. we have Felix Leopold. He's technical lead for MEV protection. Welcome, Felix.
Thank you. Hi, everyone. My name is Felix. I'm working with an awesome team of people at CowSwap, and I want to talk to you today about how we can design fairer trading mechanisms for Ethereum. And I want to frame this vision based upon an idea of just having a single price per token per block. And we'll explore a little bit of why we think this is the most fair way of trading on Ethereum. The reason why we're talking about this is if we look at main adoption of decentralized trading, we can see we've made some progress in the last couple of years, but we're just seeing the tip of the iceberg here. Even digital asset trading as a whole, including centralized exchanges, is many times larger than DEX trading today. And when we want to get into more interesting markets like the US securities market, or maybe the holy grail of trading, global foreign exchange trading, then we really need to step up our game. And I think personally that Ethereum has, as this credible neutral settlement layer, the potential of enable trading of all different parties across nations, supranational actors. So I really think this global foreign exchange trading is a goal that we can strive for. So to talk about how we get there, let's first revisit a little bit the brief history, honestly, that we had in the context of decentralized exchange trading. And I want to frame this history based upon an article from Alvin Roth, who is an expert on market design and won a Nobel Prize in economics a while ago, who wrote this essay on necessary requirements for a market to function in Harvard Business Review a while ago. And he mentions 3 properties that a market needs to at least fulfill in order to function properly. The first one is a good market needs to be thick. Thickness just meaning that there is enough liquidity that when a buyer and a seller come, or even just one side of them, they can actually interact. The second point that I will put a lot of focus on is what Alvin calls safety. And by safety, he means the market has to incentivize its participants to truthfully reveal their preferences. They shouldn't be holding behind the bush and haggling and kind of hiding their true preferences, but instead be incentivized to commit them kind of openly. And then the last point touches more on the scalability aspect, which I will not go into much detail here because we know Ethereum as a whole is focused on getting scalability done, and we have all these great talks at this conference about ZK VMs, sharding, and so the hope is that with Ethereum figuring out scaling, we can basically piggyback on that scaling for DEX trading as well. And so if we look at how everything started a couple of years ago, the first DEXs on Ethereum were EtherDelta, IDEX, or ACES, basically on-chain limit order book DEXs. And those worked fine for some token pairs, like Ether USDC maybe worked quite well, but they had a fundamental flaw, which was that they required active market-making participants to constantly update the quotes and the bids and basically keep the market flowing, keep the market in sync. And with the explosions of tokens in the space, it made it very difficult to bootstrap markets for new token participants or for new pairs. And so what the problem with on-chain limit order books was that it was just eventually very hard to create thickness, create thick markets. And this is where AMMs came along. AMMs really solved the problem of liquidity provision and allowed every one of us to become a liquidity provider just by staking 2 assets into a smart contract that would then automatically sell them on our behalf based on some curve, based on some preference curve. And all of this started in the context of prediction markets way before blockchains were born. Robin Hanson had a paper on logarithmic, basically AMMs. And then in the context of Ethereum, we had many different teams pioneering more or less complex functions. Everyone, of course, knows X times Y equals K. But really, the key thing that AMMs brought to the space was overcoming the liquidity bootstrapping problem and creating thick markets, even for long-tail tokens. So what's the problem with AMMs? The problem with AMMs, and again, we have heard many talks about this at this conference, is MEV, or how I will call it in this presentation, pay-as-bid pricing. And pay-as-bid pricing comes from the fact that what you're seeing on, for example, Uniswap, if you're trading some tokens, is not actually what you are sending into the mempool to be executed. This is a trade that actually happened a couple of weeks ago. Somebody was selling $1 million on Uniswap and probably saw on the UI that they would get 750 ETH. But the thing that you need to add on Uniswap is a discount to the current fair market price, which is referred to as slippage tolerance. And you can think about slippage tolerance as basically how much volatility are you willing to accept in order for your trade to still go through. Blockchains are asynchronous by design, so there's race conditions, and so the moment you click swap on Uniswap, somebody else might also be clicking swap somewhere else, and therefore you need to price that volatility tolerance or slippage tolerance in. Now the problem with it is, if your trade is large enough, if the slippage tolerance is large enough, the block builder, proposer, validator, miner, call them what you will, has an incentive to actually manipulate the prices and execute your trade exactly at your bid, at the bid that includes your slippage tolerance. And so this is what happened here. This person got sandwiched and lost $10,500 to the, in this case, it was after the merge, to the block producer or validator. And so this is really what makes AMMs fundamentally unsafe by design. The fact that you cannot be honest about your slippage tolerance. You basically have to lie to the AMM and say, hey, just set this small slippage tolerance because I know if I really tell you what I'm willing to accept, somebody is going to sandwich me and run over me. And so maybe to go a step back and revisit, why is it important to have a safe mechanism design here, a safe market? The first reason is that safe markets are just fundamentally simpler to reason about and make conclusions that basically the system is secure and that the allocations is optimal and you find the right answer. The second reason why safe markets are better or important is that they're fundamentally more efficient than unsafe markets. Because if users are incentivized to reveal their true preferences, you can just look at the preference and find the globally, socially optimal allocation in one round trip, rather than doing multiple bids and asks and basically haggle around the table. And then the last point is maybe a more altruistic argument that safe markets are just fundamentally fairer to the least sophisticated participants. Tarun was talking about stealing from grandmothers. I personally think more about people that visit Reddit and find a new coin and then go on Uniswap trying to trade it and basically get wrecked. And yeah, the least sophisticated participants are automatically protected in safe markets. And so I agree with Maureen O'Hara, who's a professor at Cornell, who says, especially on this problem of MEV, that blockchain is not going to succeed if it's not viewed as fair. And so let's revisit the slide that we saw in the very beginning. If we want to get larger market adoption, we need to design fairer and safer market mechanisms. So how do we build safety on top of AMMs? This is what the second part of this talk will focus on. The first thing that I want to kind of revisit is what we think is probably the fundamental root cause of most of the MEV that's out there, maybe even all MEV. And that is that a single asset today on Ethereum can have many different prices within the same block. Here's an example block from, I think, a week and a half ago, where the most liquid pair that exists on Ethereum, ETHUSD, was traded 11 times within the same block and at 8 different prices. The difference between the lowest and the highest price in this block was more than 1%. And imagine, the block really just happens at a single moment in time. That's what blockchains do. They freeze kind of the state of the world in a specific instant of time, and yet that instant of time told people, well, there's 8 different prices for the most liquid pair. And for example, latency arbitrage. When you see a price change on Binance and you try to arbitrage it away against an AMM, that is an example of MEV that comes from one asset having multiple prices. Because the first person that gets to trade in the AMM still has the outdated price available, and then everyone else in the block trades at the fair market price. We have one asset, many prices. The reason that liquidations cause MEV is because that whoever triggers the liquidation gets to trade at a discount, whereas the rest of the market trades at a different price, rather than using the liquidation volume and put it into the fair price finding and just settle everything at a single price. And then the last point, the sandwich attacks we saw on the last slide, is very obvious. There were 3 different prices, the opening, the victim, and the sandwich. Again, one asset, many prices, and that's why we have MEV. So I argue that any market structure where prices depend on arbitrary, the block producer can choose it at basically at their own will, that arbitrary interblock ordering just makes these mechanisms unsafe by design. And so what is the solution? Well, you might have guessed it from how I've started this chapter, but the solution is to just have one price per token per block. And so how would this look like? We basically, associated with every Ethereum block, have a price vector for every asset that is traded in the block, and that asset just has a single price at which it can be accessed within, well, that block. And this price here is denominated in dollars. It could theoretically be denominated in any currency you'd like. But the idea would then be that the participants that are trading in this block would be trading according to this single price clearing. So if you're trading ETH against Bitcoin in this block, you can basically get your exchange rate by just looking up the two values here, and that defines what is your exchange rate in this block. And so this idea of uniform price clearing is very tightly coupled to the idea of not executing trades sequentially, one after the other, but batching them together and executing them in one single batch. So now I want to talk about how we at CowSwap have built a batch auction system on Ethereum. We've been live for 1.5 years now, and yeah, you can actually achieve this with everything that Ethereum offers today in just 6 simple steps. The first thing that we need to do is we need to stop people from sending raw Ethereum transactions, because that's just a fundamental limitation of the protocol layer today. You cannot, when a user signs a raw transaction, you cannot open up this transaction, batch it together, or do anything with it. The user signed it, so it has to be executed as is. But trading can also be done on an intent-based. Really what you do when you sign a transaction on Uniswap, you're just saying, I want to sell token A for token B at a specific limit price. And so what we do is we collect user trades as trade intents rather than as raw transactions, and we collect them over many different token pairs. So we basically have this multi-dimensional order book of signed trade intents, which we then combine with the entirety of on-chain liquidity that exists on Ethereum today. So all the AMMs you know about, all the RFQ systems you know about, and that together creates a thick market. We saw earlier that AMMs are really responsible for the thickness, and so by adding user orders to that liquidity pool, we have the first criteria, which is a thick market. We then go ahead and now trying to find a settlement in which ordering doesn't make any difference, in which at least all user trades are executed according to one single price clearing vector, where each asset just has a single price. And so basically we want to find a uniform price clearing, and we also need to find a concrete execution path. So basically meaning, where do the tokens flow so that demand and supply equal, basically that we reach an equilibrium. In this case, for example, the maker token that the first user wanted to sell would flow directly to another user. That user would sell their USDC maybe on Curve to DAI, and then give it to the third user. And so we can, in so-called ring trades, mix and match AMMs together with direct peer-to-peer trading, with the only constraint that everything has to happen, at least everything between those hands has to happen at this uniform price clearing. Now the problem is that this poses a pretty hard optimization problem. It's basically an NP-hard problem because we're acting over multiple dimensions, not just on a 2-dimensional order book. But this problem can be quite well approximated, or the optimal solution can be quite well approximated if we just maximize the total user surplus. User surplus is basically the price improvement you get on the user's limit price. So if a user was willing to buy Ether at $1,300 and you were delivering it at $1,250, you would have given $50 of surplus to that user. And if we sum all the surpluses up together, we get one value, which we can optimize for. And by having this optimization criterion, we can now dispatch this hard problem to a network of what we originally called solvers. Now we're starting to call it batch builders, who are basically tasked to try to find the most optimal solution to this problem. And they could employ very different strategies or heuristics. Here we saw the settlement from the previous slide, but you could have a solver that just goes and tries to settle every single user trade with the most liquid AMM on that pair. But by virtue of having this approximation criterion or optimization criterion, we can now rank the different solutions and find the one that settles the user trade at the best possible price. And then that solution will get chosen, and the proposer for that solution gets a protocol reward. And so we kind of moved into a consensus scheme where the leader selection is not based on work, not based on stake, but based on optimality. And so how does this work in practice? So we said CowSwap has been live for 1.5 years. The UI looks very much similar to what you might be used from your favorite AMM frontend. But here's an example of a batch that we saw, I think, around 20 days ago, where two users were trading in the same. So we can see there's one high-level Ethereum transaction, but in that single transaction, we have two people trading two trade intents. So we have one person that is selling the manifold token and another person that is buying the manifold token. And the first thing to notice here is that both people were executed at the exact same clearing price. Whereas if they had gone through a more traditional DEX mechanism, one of them would have to go first and get a different price than the second one. In this case, it was actually better to be the second because the prices, the trades were against one another. So you want to first have the other person move the price in your favor and then trade. But basically, by matching those at a single uniform clearing price, we removed all the games that the people in the batch could have played against one another and made the system more simple, fair, and safe to reason about. The other thing that is cool is that because these tokens were traded exactly in the opposite direction, which is what we call a coincidence of wants, you want the exact opposite of what I have, we actually saved about $40,000 in trading volume that we didn't have to send to Uniswap and SushiSwap because it could be settled directly peer-to-peer. So here we have one person buying 40,000 USDC and one person selling 48,000 USDC. And so in this specific example, we actually not only got fairer pricing, we also got a structural price improvement that only batching people together and trading people peer-to-peer can accomplish. Because we saved so much money that didn't have to go to the AMM, we saved about $800 in reduced LP fees, and we also saved about $1,500 in reduced price impact, which stems from the fact when you trade against an AMM, you're moving the price up, and then when you sell against it, you will move the price down again. And so this is how the solver competition I talked about is looking at the moment. We have, as of last week, we had 12 solvers in production. As of this week, we have 13 solvers in production that are competing for finding the best solution. So we actually have quite a heterogeneous landscape of different solver entities. And then there's an entire presentation from our data engineer, Gent, that was given at Devcon, which I highly recommend watching, which compares the performance of CowSwap in terms of how much slippage can we actually, how much of the slippage can we actually give back to the user compared to other DEX aggregators in the space. And we can show that we have substantially better performance compared to some of the other DEX aggregators. So for the last couple of minutes, I want to talk a little bit about proposer-builder separation, or kind of the general direction I think that the ecosystem is taking with regards to MEV, and why that could be, or why I think this is dangerous. And I want to start this by quoting one of my favorite columnists, the Money Stuff BBC writer Matt Levine, who is from time to time repeating that, well, crypto is in the business of constantly rediscovering the basic ideas of financial history. And why I think this is true specifically for PBS is, well, I'll talk about this in the next few slides, but you might have seen this graph before. This is basically trying to resemble the MEV supply chain, going from a user that wants to make a trade, the trade being something like, I want to sell USDC for ETH, opening their favorite wallet or opening their favorite dApp, which converts that trade intent into a transaction and sends that transaction in PBS to a network of block builders. The transaction will be something concrete, like use Uniswap to sell $1,000, for example. And then those block builders will try to collect transactions from a bunch of different places and propose a block to the actual leader of the consensus protocol, the validator for the next block. And so the validator is posed with a bunch of choices of blocks that they can pick from. And basically, the block builders are bribing the block proposer to accept their block by doing a max bidding kind of war. And this meme is from John, I have to give credits. So how does a block builder actually get the money to perform this bidding? Basically, block builders try to extract as much MEV from the transaction order flow they get, and then pay back some or most of that in this max bidding war to the block builder. So what might a block builder do in order to get an edge in this game? Well, they might try to find deals with wallets to get exclusive access to order flow. If they are the only one who can extract value, or even just pose this transaction for its transaction fee into the block that they propose, they have an advantage over other block builders. And so it could be that the flow just stops here. Wallets are starting to receive an extra income. That's nice. They might take that. That would be very terrible for the user. Maybe in a slightly better world, the wallets will pay back some of that returns to the user and maybe give the user something like free transactions or commission-free trading at least. But if we're in this world, then we've literally just reinvented traditional finance. Because the brokers such as Robinhood, receive payment for order flow from market makers or wholesalers, such as Citadel Securities, Jump, Jane Street, but it's just really a handful, and then offer commission-free trading to their end users. And I'm not saying that PFOF is bad. Actually, in traditional finance, there's arguments on each side. But what I try to stress here is that we've learned from traditional finance that this mechanism doesn't work in a decentralized fashion. Market maker, there's just a handful of them. They're highly regulated. Without the SEC, users would be run over. There's basically this law that requires market maker to give people a price improvement on top of the official bid and ask that they see on NASDAQ and New York Stock Exchange. So you require regulation in order to make this market safe for the user, and it is just a centralized system. So if we really want to get Ethereum to be this neutral, credible neutral settlement layer, we cannot reinvent the system and work with traditional finance. The other thing that I hear a lot is, this narrative around MEV maximization is great. We all have to focus on MEV maximization. Sure, we should minimize, but we need to maximize the shit of what's out there. And I just want to pose the question of these two philosophies, MEV maximization and minimization, can coexist at the same time. Because, at least in my mind, MEV maximization leads to very dangerous incentives for the participants and creates an extremely hard coordination problem that MEV minimizing protocols such as CowSwap need to overcome. Right now, we are in a, you could think of a MEV reducing protocol or an MEV reducing builder to having to play a repetitive prisoner's dilemma, where in the current status quo, everyone is extracting MEV, so everyone is making a little profit. If you now were a block builder that wanted to operate without the rent from MEV, you would deflect from the extraction, but you would basically not get any rewards from MEV, and everyone else would get slightly more. And it would require the entire space, all builders, to cooperate in order to achieve a new equilibrium in which we'll actually, hopefully, are all socially better off. Definitely the people that are trading because they are not getting wrecked, but even the people that are validating, I'd argue that in this system can make much more money from transaction fees and just adoption. But really this requires all builders to cooperate, otherwise we'll not get into this new equilibrium, and what we see today is that basically everyone is focusing on the top left corner, and the status quo is to fight over the existing MEV that's in there, and potentially even fight against new entrants that are trying to propose MEV reducing protocols, because basically that's eating the searcher's lunch. And so my call to action here at the end is, let's not focus on MEV maximization and split the pie that's out there because it's tiny compared to what we want to unlock. Let's work together and grow the pie and try to get Ethereum to the next order of magnitude of adoption. And with that, thank you very much.
Thank you, Felix. Does anyone have some questions?
There we go. All right. Hey, great talk, by the way. So I have a kind of a quick question, right? Like, what you've done is you've taken a hard problem, you have made it an NP hard problem. You have an NP hard problem, which is like this very complicated auction, which brings a bit of a difficult situation because NP hard problems kind of by definition are very sensitive to like people kind of manipulating things and adding solutions. And I think, if I recall correctly, Bancor had some interesting issues with this. So why not, for example, one simple condition to have one price for many assets, or sorry, one price for many dexes for specific assets is just to do optimal routing. And optimal routing is a convex problem. You can do it efficiently. It's very simple to solve. Why not just do that instead?
Yeah. So I think just having one price per token pair per block is, I think, what you're suggesting. That would already be a huge improvement to the status quo, and it would be very computationally feasible to solve. I totally agree with that. I think the reason why we're aiming for multi-dimensional batch auctions is to make the life of our solver team harder, of course, but also to because we know that, or we've seen that the token space is just absolutely fragmented, right? There's no cost for somebody to launch a token, and so even if we just look at US dollars, there's 10 or 15 different stablecoins that are all trying to resemble the US dollar. And so sure, we might have then one price per token pair on USD ETH and DAI ETH and LUSD ETH, but we would still have this implicit fragmentation and this implicit arbitrage. And so we think the most efficient way of of arbitraging if USDC to DAI is 1.1 and then ETH DAI is 1300 and ETH USDC is 1200, you still have like some imbalance in that. Right, and so I mean I agree with you. It's a good first step maybe, but we kind of already aimed for the second. The holy grail is refragmenting re-aggregating the fragmented liquidity space that we have on Ethereum, and therefore we went multidimensional.
Great talk. I think like one question on kind of like seeing liquidity fragment between L1s and L2s. How do you see it kind of like is there a way on how CoSwap could settle like cross layer 1, like cross layer 2s? Because I think like, yeah, it's probably like the next problem in like MEV.
Yeah, I mean, yeah, we are definitely, I think one problem that we're trying to solve rather sooner than later is to just access liquidity on another chain through the solver abstraction. So right now, if you're, for example, trading on Polygon a large amount, you have to potentially bridge to mainnet, trade there, bridge back, and that's kind of annoying from a user perspective. Because we already have this abstraction of solvers, that can just happen under the hood, right? The solver can do the bridging, swapping, bridging back for you and just, needs to let you know that you might have to wait a little bit longer, but you as a user don't have to worry about it. But then, of course, the true holy grail is to just have one price per token per block across many chains. I think it's a very interesting research problem where we've touched the surface on, but not gone super deep yet. Synchronicity between chains, maybe you have to do some locking of funds. There's actually, Mohammed is sitting in the crowd, there's actually a hackathon project at ETH Amsterdam that looked a little bit into this, but yeah, it's very early days for that, so nothing that you could build on right now.
Thank you, Felix.
Thank you.
Remember, there will be an after party after the closing ceremony, so join us, please. And the last talk, we have Theo Diamandis. He's researcher at Bain Capital Crypto, and wow, MIT PhD student. Welcome, Theo.
Thank you. All right, hi everyone, my name's Theo. I think I'm going to steal proof of optimality in this talk from Felix's talk because I really loved that. But today we are not going to talk about DeFi, we're going to talk about multidimensional fee markets, or kind of the fancy term is how to do dynamic pricing for non-fungible resources. And this is joint work with Alex Evans, Tarun Chitra, and Guillermo Angeres. All right, so the first thing I hope to convince you of is that fee markets with a joint unit of account, like gas, are actually pretty inefficient. And what we're going to slowly work towards in this talk is a framework to optimally set multidimensional fees. So first part of this is like, why are transactions so expensive? Why is having one market not necessarily something that you want to do? And first, a little bit of an aside, one of the things that we actually do sometimes see with one-dimensional fee markets are these types of denial of service attacks. And this is because all opcodes have fixed relative prices to each other. And whenever you have a potential mismatch between a relative price and the resources that that opcode consumes, you can get something that takes down a network. So these have been termed resource exhaustion attacks in the literature. And there was a famous one back in 2016 that took down the Ethereum network, or essentially made it unusable. Did not take it down, but made it very hard to use for quite some time. And this was essentially due to a disk read mispricing. And of course, this was patched in a subsequent EIP. But if we had a multi-dimensional rather than a single-dimensional market, we might have been able to adjust prices such that there was no need to actually reprice the opcodes after the fact. However, what we're going to concentrate a little bit more on today is throughput, is why having a single-dimensional market is actually bad from kind of a network designer's perspective. And so this is a very, very stylized example that is not at all like close to in practice, but I hope it illustrates the idea. Let's assume that we have a bunch of users that are submitting transactions. Some only consume CPU, some only consume bandwidth. The CPU ones have some utility of 4, so that's kind of how much utility they give to the user that submits it. And the bandwidth ones have utility of 2. And let's imagine we have a block. Each of these transactions costs 1 gas. The gas price is 3. And the block can fit 4 CPU transactions and 4 bandwidth transactions. Well, in a single-dimensional market, what happens? We fill this up with CPU transactions, but actually we have a lot of block space that's not used because these bandwidth transactions aren't high enough utility. And something like this can happen, say, with like an NFT mint. However, if we have a 2D market, and say CPU has that cost of 3, but bandwidth has a cost of 1, we would actually end up filling up all the CPU transactions in this block and filling up all the bandwidth transactions as well. Like I said, this is a very stylized example, but it does illustrate when you price things separately, or in other words, if resources are orthogonal, they should be priced separately. However, that of course we need a mechanism for price discovery to do this. So how do we decide that CPU is 3 and bandwidth is 1, or what are those prices? What do those prices even mean? And how do we get to those prices? And I'm going to do a little bit of an aside in that I've been throwing around this term resource a lot, and there's a question of like, what exactly do I mean by that? The working definition we're going to use for this talk is anything that can be metered. So a resource is anything that I can say how much of this thing a transaction uses. So for example, one thing right now, roll-up data. However, we could also talk about like kind of big resources like compute, memory, and storage. We could go down to the opcode level and think of each individual opcode as a resource. However, we could also say, sequences of opcodes are resources. For instance, if you're calling like a hot storage slot versus a cold storage slot, that's going to be cheaper. So maybe if we have several storage opcodes all in a row, that's actually a different resource than calling these one by one. Furthermore, if we're running full nodes on multi-core machines, maybe compute on like on core 1 is a different resource than compute on core 2. And so on. You can imagine this is a very general construction. Resources can be very dependent on each other. And so as long as they can be metered, or we can say how much of a resource a transaction uses, that fits into our framework. So to formalize this, and this is kind of where we get a little bit into the math, we're going to say a transaction J consumes some vector of resources. And there's so M resources, and this vector is AJ. So essentially, the ith element of that vector is going to be the amount of resource I consumed by this transaction j. And now that we're starting to build blocks, we're going to denote this vector x that essentially is this 0, 1 vector. And we have n transactions. Xj is going to be 1 if that transaction is included in a block, and 0 otherwise. So this allows us to very easily write kind of the quantity of resources that's consumed by a given block, and we're going to denote that y. And all this is summing up the vector of resources that's consumed by a particular transaction times xj. And xj, if it's 0, then we're not going to include this in the sum. If it's 1, then it's going to be included in the sum. And this can be written in kind of this very convenient matrix vector notation as well, where the columns of A are going to be the transaction vector, or the resource vectors for each transaction. All right, so now that we kind of have a notion of a resource and what each resource is, we can talk about things about constraining resources, targets for resources, and charging for each individual resource. So we're going to first define a resource target. And that's going to be this B star. And then the deviation of the target, based on what I introduced earlier, is just AX minus B. Remember, AX is the quantity of, or the resource utilization of a particular block. And in Ethereum, this is one-dimensional, so this is going to be a scalar, and B star is just 15 million gas. We also want sometimes a resource limit that says how much, or after a certain point, a block is invalid, and then we can have transactions satisfy something like this, where AX has to be less than or equal to B. In Ethereum, this is 30 million gas. So again, in Ethereum, this is all one-dimensional. However, we're extending this to a multi-dimensional case. Finally, this allows us to talk about prices for each resource. So we're going to have some vector P. This is going to be an M vector, and Pi is essentially going to be the resource price of, or the price of resource I. So that allows us to very easily write how much a transaction costs, which is just the dot product of its resource vector and P, and then this is split up into the sum here. One thing here is when I talk about prices, this is going to be the amount burned by the network, or essentially the price that the network charges for a given resource. So think like EIP 1559. It's not actually going to be the price that users pay, say, validators for inclusion in a block. So nothing about tips here. This is just going to be purely the amount that's burned. All right, so we set up all the math, which is great, but we still have to go back and say, well, how do we actually determine how to charge for each resource? Now, there's a number of very reasonable things that we want. If the utilization that we have is equal to our target utilization, we probably don't want a price to update. That seems to be kind of like a good price. However, if we're over the target utilization, we would want the price of that resource to increase because we want to make it more expensive so people decrease their usage. And if we're under, kind of vice versa. So a number of things have been proposed kind of to this end. One proposal from the Ethereum research forums back in January was this price update rule here. You can kind of go through and basically see that it does satisfy these properties that we want. However, I could write down a bunch of other price update rules that also satisfy these properties. So this kind of begs the question, is this a good update rule? Or like, what is this update rule actually doing? Are there other update rules that are better or have different behavior? How do we go about analyzing this? And kind of the punchline of this talk is that all these update rules are actually implicitly solving an optimization problem. And a specific choice of the objective, which you can think of as how the network designer wants the network to perform of that optimization problem, is going to then give you a price update rule. So this means, essentially what I kind of want to convey is a good way to think about price update rules is not like, oh, how do I design the best price update rule? It's what do I actually want the network behavior to be? So kind of what is my objective? And then from there, we'll show how to get to the price update rule. All right. So this brings us to what we call the resource allocation problem. And the setting for now is we're going to pretend the network designer is omniscient and gets to choose all the transactions in each block. I know this is entirely unrealistic, or not even unrealistic, it's just absolutely false. However, this is going to allow us to build up a very useful mathematical problem that's going to get us to the price update rule. So there's a few things that we need for this problem. First, we want a loss function that's defined by the network designer. And this loss function essentially is going to be the unhappiness with the current resource utilization. So there's a few very reasonable or potentially kind of silly loss functions that we could choose. One is this, so the loss function of y. Remember, y is going to be the resource utilization of a given block. Maybe it's 0 if we're exactly at our target, and it's infinity otherwise. Another thing we could do is we could say that actually we don't care if we're under the target, we only care if we're over the target. So we can say, okay, the loss is 0 if we're under the target, and it's infinity otherwise. Again, these might not be what you actually want to do in practice. Potentially, you want to have something where if you're a little bit off the target, you're not that unhappy, and then it grows, say, quadratically as your deviation increases. But the whole point is we only need something that tells us kind of the unhappiness with the current resource utilization. Then we need some way to say, what is the set of allowable transactions? And in this, we're going to encode all constraints in this set S. So this is going to be this binary set that encodes things like network constraints. So like earlier, a block in Ethereum is invalid if it's over 30 million gas. However, there's a lot of complex interactions among transactions as well. So for instance, if a lot of searchers are all trying to get a specific liquidation, only one of them can get that liquidation. And this can also be encoded in this set. So this is a very general kind of object that just says what transactions are OK. We're going to do, this is kind of the first mathematical trick that we play here. And this isn't that important, but it's essentially, instead of considering S, we consider what's called the convex hull of S. This just means that instead of forcing x to be 0 or 1, we allow x to be a fractional value between 0 and 1. So the way to think about this, and the way this kind of makes sense, is from the network designer's perspective, you care more about the average case or the average kind of usage of the network, not one particular block. So say if xj is a fraction, that would say that we include that transaction after roughly 1 over xj blocks. And we'll see that we can actually remove this constraint in a little bit. But again, this is just to set up kind of the mathematical formalism. So this doesn't really this won't really matter in a bit, but I just want to be complete. All right, the final thing that we need is we want to know how much utility a given transaction gives to the joint user and validator set. We group these two parties together into what we call the transaction producers. And the reason we do this is because we don't want to deal with kind of the game theoretic analysis of looking at bids and auctions and that type of thing. So we assume that kind of this group of people is together, they're submitting transactions, and those have a specific type of utility. You'll see that our mechanism actually doesn't matter that we group these things into the transaction producers, but this does present an area for future work. And I'd like to point out that we almost never know Q in practice. It's more or less impossible to know that. However, we will see that this actually doesn't matter once we write out this problem. OK, so a lot of setup, I'm sorry. But this is kind of where we get to. So what is the resource allocation problem? It is to maximize the utility of transactions minus the loss that the network has, subject to kind of the resource utilization being defined by the included transactions and the transactions being allowable. So this is the ideal kind of best case scenario of what we would actually like to solve. For all the reasons I mentioned earlier, this is not something that we can actually solve in practice, but we'll see that it turns out to be a very useful starting point. And again, this is because the network designer doesn't say which transactions are included, Q is unknowable, you can't partially include transactions, all of these issues. However, we'll see that we can actually pull from a branch of math called convex analysis, and specifically duality theory, to take this problem and turn it into a way to set prices so that the validators and users, or the transaction producers, implicitly solve that optimization problem without the network designer needing to really do anything. Just update prices in a very simple way. All right, so the 30-second version of duality theory is essentially it allows us a way to relax constraints into penalties. So I can say that you actually don't have to satisfy this constraint. You just have to pay for every unit of violation. And this allows us to take Y, which is what the network designer cares about, that's the throughput, and decouple it from the transactions that are actually included in the block. There's just going to be a penalty for these two things not matching exactly. However, what strong duality tells us is that if we correctly set the penalty, this penalty being the prices, then the dual problem is going to be equivalent to the original being this problem, which is what we actually want to solve, and these two utilizations are going to be equal, and they're going to have the same optimal value. So again, this tells us we correctly set the prices, and we solve this problem without having to know Q, without caring about the fractional transactions, without all the things that I mentioned are issues. All right, so kind of turn the crank of the math a little bit, and you can decompose this dual problem. So the dual problem is to maximize this thing, or sorry, to minimize this thing into a network problem and a block building problem. And P is going to be the dual variable that's going to connect these two problems together. So again, those are the prices, and the prices are essentially a penalty that we pay per unit violation of this constraint. This first term here is actually easy to evaluate. You'll probably just have to trust me on this. It's this object called differential conjugate. It's something that we have in closed form, and that means that essentially this can be run on chain. However, the second term is a little bit more interesting, so let's look at it in a little bit more detail. What is the second term actually saying? Well, it's saying maximize the utility minus the cost, so this is the net utility, subject to the transactions that we can actually include. This actually has the same optimal value if we just use S instead of the convex Hall of S. And this is exactly the problem that is solved by the block producers. So what does this mean? The network never has to solve this problem. It could just observe from the previous block which transactions were actually included, and then it kind of gets the solution of this for free from kind of the decentralized block builders. So what do we get at optimality? Well, if we assume the prices are set correctly, so that's going to be P star, and then the block builders use those prices to include essentially the transactions that are optimal, then what do we get? Well, we get that the resource utilization of the network is exactly equal to that of the block. Again, that's back to what I was saying earlier, is that we essentially get that this constraint does hold at optimality. And Y satisfies this, which we can look in a little bit more detail. What this means is essentially the prices that minimize G, so this is the dual problem, charge the transaction producers exactly the marginal cost faced by the network. So if you set the prices optimally, for whatever loss function that you define, the marginal cost of using more of that resource is exactly what the price is that you charge. Furthermore, these prices are going to be the ones that incentivize the transaction producers to include transactions that maximize welfare generated minus the loss incurred by the network. So that's back to that original optimization problem that we saw. You correctly set prices, you solve that problem. The network designer doesn't need to know the utilities or anything like that. All right, so, okay, that's great. I still haven't told you how to choose prices. I've just kind of talked around this for a while. So how do you actually do this? Well, we can compute the gradient, exactly. And what is this? Well, essentially, the network can determine this Y star, and I said earlier that this is computationally easy. Then this X star at some current price is found by observing the transactions in the previous block. So then all we do is we apply our favorite optimization method, like gradient descent, and we update the prices using this gradient up here. There's a lot of other optimization methods that you could choose here. They're going to have different convergence behavior and different trade-offs between, say, convergence and complexity. This is all stuff that we leave for future work. Just to go through simple examples of what I showed earlier. So let's say you had this loss function, looks kind of silly. You actually do get somewhat of a reasonable update. So this looks like the residual. So you essentially just update your prices by some fraction of the residual. If you use this one, where you're only unhappy if you're over the utilization, you have the same update, except you essentially make it so these are non-negative. So if any of these are negative, you zero them out. And so you can actually see that this makes sense. Here, in this first loss function, we're unhappy if we're under the utilization. So this means that we might actually want negative prices to incentivize people to use more of a particular resource. Here, though, we actually don't care if we're underutilizing based on our target, so we're never going to have negative prices. And again, this is to kind of get to the point that the network designer chooses the loss function, and the loss function encodes exactly what your unhappiness is with a particular resource utilization. And then once you do that, update rules that will minimize that loss function will fall out of it. So it comes down to, instead of choosing what the update rule is, you're choosing what the loss function is. All right, so this is a lot of math. We did some numerical work to kind of see how this would work in very simple examples. So here we have kind of a steady state behavior of a network with only one type of transaction that's being submitted. You can think of this as pretty analogous to that example that I showed at the beginning of the talk. But you can see that one-dimensional prices are doing about 10 transactions per block, and multi-dimensional prices are able to eke out maybe like 2 to 3 more transactions per block. But this is even when it's the same type of transaction that's going through. So even this kind of like the simplest case, you get some improvement from using these multi-dimensional prices. And I'm not going to go through all the details of kind of how we set this up, but I'd encourage you to look at the paper for that. However, where this really shines is when we have a distribution shift. So in this example, what we did is we have this type 1 of transactions, which you saw earlier, but we add this type 2 transaction, which has a much different resource profile. So you can think of this like an NFT mint or something, and they come at about block 10. So the multi-dimensional prices are the purple and blue, and you can kind of see that there's this nice spike here where we do less of type 1 transaction, more of type 2, and then kind of once we go through all of these, we return to 0, and we clear some backlog after we've gone through these. You could also see on the right here, these are the multi-dimensional prices. So once we hit block 10 and the distribution shifts a lot, this light blue price goes down, the other price goes up quite a bit, and then they return to a steady state a little bit afterwards. Again, the uniform prices are still able to adjust to a certain extent, but it's going to be less throughput overall. And back to what I was talking about earlier, where you have some target utilization that you want to use, you can see here in this second example, the dashed lines are going to be the targets. So the multi-dimensional prices, which is the top, deviate from the target for a short period of time to handle kind of the big spike in transactions, but then the network returns to steady state afterwards. In the uniform prices, where you can think of you have less dimensions for this controller, you essentially get this oscillating behavior, and you eventually return to somewhat of a steady state, but you kind of get a lot of a mess right here as the distribution shifts. Cool. So there's a lot of future work to be done here. One thing that we didn't do is super extensive numerical examples, and you can imagine that using real data here might lead to valuable insights that allow you to tweak the framework in specific ways. In addition, like I mentioned earlier, we group the transaction producers, or we group the users and validators into that transaction producer kind of set. And there is some work on the dynamical behavior of like essentially how do we make this strategy proof? How do we we just talked about essentially the amount that was burned by the network in our prices. So how do we kind of make this into an entire system? Also, I mentioned earlier that the update rule, while I chose gradient descent here, there's a lot of other things that you could do. You could actually choose the update rule in a way that gets you something that looks very, very similar to what was proposed on the Ethereum research forums back in January. And there's a question of, okay, well, which update rules are good, which update rules are the most useful, and how do you trade off between, say, convergence behavior and complexity? So how quickly kind of your prices can adjust, and how much work that you're doing on chain. Then, of course, on the system designer side, so if you're actually trying to use this in practice, there's a lot of questions that this general framework doesn't totally answer. So for example, like, what should the actual resources be in a given system, and how do you trade off kind of the complexity, pricing every opcode, every sequence of opcodes, and so on, and the ease of use of these things? And then, of course, how do you determine a loss function for the desired performance characteristics? Again, kind of the very important point here is that system designers should be thinking about these questions, but should not necessarily be thinking about, okay, well, like, how do I do the exact update rule for prices? Because in this framework, if you think about these questions, then the update rule falls out quite naturally. All right, and I encourage you to check out the paper, which has a lot more and is kind of like 38 pages that goes through this entire thing in excruciating detail. And happy to take any questions. Thank you.
One, two, yeah. Seeing as in your models, you're willing to give different costs to different opcode and resources and everything, I think something that could be interesting to see is the order of a transaction itself, if I have different costs or not, especially of storage. Like, for example, I know that MEV is a thing, and generally speaking, if you hit a storage slot earlier, it has much more potential value because this means you're being settled first. What would be the impact of costing differently the storage of code depending on where you are in the block? And generally speaking, in terms of resource utilization too, anything that happened earlier in the chain is more costly for the network as a whole because you need to store it for longer. And I don't think your framework is straight up compatible with this costing because it's missing one dimension on the vector of cost. Maybe I'm wrong.
Yeah, no, that's actually a great question. I think it's compatible with the first, but not necessarily the second. Or the second one you could probably put into it, but it would be a little bit harder, this kind of multi-block one. However, for a single block, you could actually view, that set S saying like, this transaction goes before this one, or this transaction goes after this one, and then perhaps if you're the second transaction in the block, you're actually using a different resource. So you're using like the second read of the slot.
That would be extremely beneficial, I feel, for a network if you can convince more people of going this direction, because this means lower cost for everyone and better utilization for everyone. So very good direction. I'm really happy to see.
I'm not saying it's easy to implement, though.
Oh, no, it's not. It's very difficult to implement, but if even the theory break, like the implementation is not going to be possible.
Thank you.
So do you see this research being applied directly, for example, in Ethereum in, like, I don't know, 50 years or maybe sooner?
I think there's probably some people in this room that could answer that better than I can. But I think we've gotten a lot of interest from different protocols that are, roll-ups, et cetera, that are interested in this, and from the Ethereum research team as well. I can't speak to development timelines, though, and when this stuff would be. Like I said, there's definitely quite a bit of future work that has to go into making this production ready. And I imagine that, newer chains that maybe aren't as don't have to pressure test their changes quite as much will probably adopt something like this before Ethereum would.
Thank you.
Hey, Theo. So in the interest of keeping this a convex optimization problem, are there any limitations this puts on how we can construct different parts of the problem, so such as the loss landscape? Or have I missed something, and is there kind of a chance we can land in a local optimum rather than a global optimum here?
Also a good question. Well, so the loss function has to be convex. So there's one immediate thing that you have from, and you can imagine that maybe, I don't know, if there's two states that you want to run in, and maybe sometimes you want to go hit for one target, sometimes you want to hit another, that wouldn't be convex if you your landscape looks like something like this. So there definitely are limitations. The other thing here is we kind of have this, the resource part is very general, and to the question earlier that you can kind of have these resources that are dependent, so like one transaction can be dependent on another. However, we do encode this all in like an additive linear way, and that's probably not the most efficient thing to do for the reasons that I talked about earlier, is you kind of get this exploding complexity as you do that. However, if you don't do that, you get to kind of the non-convex world. So it might be a more succinct or lower complexity way of describing what it is that you want to do, but you won't actually be able to solve it. And this entire framework does rely on strong duality, which you only really get in you mostly only get it in convex optimization problems, or it's very rare to get it in non-convex problems. And that allows us to look at the prices, which is kind of the dual of that. Instead of looking at like what transactions do I include, I look at how do I set prices. But yeah, that's a great question.
Awesome, thank you.
Thank you, Theo.
Thank you.
And now, people, let's go to the top of the mountain to find where is going to be Devcon 7. See you there.